second espresso?
Okay.
But you want?
I'm not sure why I want that set.
Okay, I can offer one today because I feel bad not having offered him anything.
Yeah.
Full. Yes, we have to.
Introduce yourself? What? You want to introduce yourself?
Ah, should I?
I think you have 5 minutes also, that's not...
We need to keep an eye on the refill of the stickers.
Yeah.
Hold it like this.
What?
That's so high.
Ooh, fancy. Oh ja, da sind die Gefahren.
Oh, there
Oh,
also
there's
one.
even 5 minutes. Okay.
So I can give you that when you start.
Do you think I should be introducing myself? And what do you think I should say? I'm one of the organizers.
You have your name on the slide. Maybe on labs. Maybe whatever title you want to have. But you have 5 minutes, so you don't have a lot of time.
I have plenty of
5
time.
minutes for all your titles.
That's not a lot of time. I know, I only have to feel like it's only the usual is the, oh, this is on you. When people enter, when people leave, they're loud, blah, blah, blah,
Yeah.
blah. Fucking yell them down.
Yeah.
I know you don't like it.
No, it's fine.
Possible to you. Oh,
Yeah,
I know it's uncomfortable.
I remember it.
And if someone has more of a comment or rather than question, what the fuck is it?
Yeah. So, 1 minute?
Oh. Ich schau einmal kurz, ob wir...
Okay.
Ja? Okay. We make one more slide.
Well, this is fine. This is fine. So as long as people stand within these, yeah. You see the cover? As long as people stay within these.
Ah, okay. Ah, you see, I see.
Yeah. So you can open that. You wanna log in? Then you can set up time.
Ah, this is, I see that.
Okay. Okay. Is this okay sound-wise? Can you hear me? Seems a little bit okay. Okay. So, for those who don't know, those rooms are super loud up front because the acoustics were made for a time before we had like electronics and microphones and such. So anything you say back there is really, really loud up front and really amplifies in both directions. This is going to be super short and sweet. I've been asked to introduce myself. I'm Richie, FOSDEM staff for like a decade or two. I've run this for like 10 years now. The staff room, yeah. So, welcome. This is the 9th monitoring and observability dev room in a row. It is by now one of the most longest running. And yeah, you're here. Transparency notice, over the years, because people left, people did things, whatever. As of right now, Grafana is the only, like everyone who organizes this specific dev room works at Grafana for one reason or another. You will see that this is not reflected in the talk selection, that we are very, very deliberate about keeping this completely fair open source without any corporate influence. There is usually themes, and for the third year in a row, the theme is not the new and the exciting. It is much more about making all of this technology actually able to use for people and actually valuable, instead of just showing everyone, oh, there is the new big thing. Yeah, stickers. There is a sticker swap table here. Feel free to take or leave whatever you want sticker-wise. The only hard rule is don't put any stickers on anything USB. Like your laptop, your forehead, we don't care, but not on anything USB, because speaking as staff, some volunteer will have to scrape that sticker off, or else USB will notice and they will be not super nice to us. They hate stickers. We like stickers. So a little bit of etiquette. If you find trash as you leave, as you enter, as you do anything, congratulations, this is now your trash. You own it. And there is where you collect your trash. Because anything which you don't pick up, it's basically going to be Carl and Fabian, because I'm not going to be here in a few minutes, who are going to pick everything up and clean everything up. So please do them a favor and just take any trash you find, even if it's not your own. Also, on etiquette, if any of you, and I mean, I realize that it's the morning after heavy beer drinking, so not everyone is hearing this, but if you have more of a question than a comment, we will absolutely, 100%, have more of a shut up than you actually getting to speak. If you want to have a little bit of a lightning talk yourself, please submit to the CFP. It's highly disrespectful to the speaker to basically, the speaker is done and then someone is like, yeah, everything you just said is wrong and this is my grandstanding. Don't. Along the same lines, speakers do all of this for free and we try to maximize the Q&A. And this means that as you enter and as you leave, you have to be really quiet. So this means no chit-chatting, no anything as you enter or leave, because else we can't run the Q&A up front here. Because again, it is super, super loud and the speakers can't hear anything if you bang the chairs or anything. And again, if need be, we will remind everyone loudly that they please need to be quiet. If there's anything, code of conduct, find anyone with a blue shirt for the intents and purposes of this dev room, or for the intents and purposes of all of FOSDEM, anyone with a yellow shirt or jacket, and we will take care of it. And that's it. Thank you, and have fun today.
This one? Okay.
Yeah, whichever.
What is the SDNI cable?
This one.
Do this and you might be answer. Just say something?
Hello, hello. Oh, okay. Thanks.
I will show you this 5 minutes before your...
Give me a second. Is it? Ah, it's
Yeah.
okay. Sorry.
I will show you this when you have only 5 minutes.
Nice. Thanks.
Okay.
As a reminder, hello? 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 Is it on? Okay, sweet. So as a reminder, before the session starts, decide if you want the table up or down. Don't be thinking with this during the talk, because no one is going to hear anything. You're allowed to leave during Q&A, but please only do so if you really, really have to. Because otherwise the Q&A is going to be completely ruined by all the sounds. So if you can, please sit down and let the speaker answer the questions. And we need to respect the time schedule due to all the recordings. This is probably the most people we had in the first session on a Sunday.
And now we have like a couple of awkward minutes.
First. So the first speak is going to be Jose Gomez Celas, who's going to be talking about the discovering the magic behind open telemetry instrumentation. And we're going to start in 1 minute. Saves us a lot of time when doing the video analytics or like cutting later if we stick to the time schedule. So we're going to try to do that.
It's okay.
But introduction is kind of mode when watching it online later.
Yeah. Oh, this too?
Yeah.
Okay.
Okay, give it up for you all say.
Thank you. Thank you, folks. Good morning. Thank you for being here so early on a Sunday. Yesterday, maybe it was hard for you. It was not that hard for me, but just a bit. So here, we're here to talk about OpenTelemetry instrumentation. I was supposed to be giving this talk with my friend Israel, but he cannot come today. Maybe it's because he went viral a couple of days ago when he got a job offer from a recruiter asking him for 3 years of experience in DeepSeek, which is pretty weird. So now he's famous and he cannot come. Yeah, and you are stuck with me. And I'm Jose. I work now as product lead at Victoria Metrics. In case you didn't know, there is a cloud product. I also work at the university teaching physics to some vet students in Madrid, in Spain. And yeah, I have a past like everybody does. And I also love playing heavy metal and sim racing. So if you do these things and you want to talk about them later, that would be super cool as well. So we are here to talk about instrumentation and OpenTelemetry. So you will be hearing this a lot, so I will try to make it super quick. OpenTelemetry is this project is super huge and gives you APIs, SDKs, and tools to understand or to create observability, and this means metrics, logs, and traces. So things start to get a bit complicated and overwhelming because this means that these APIs, SDKs, and tools need to produce or ingest and show metrics, logs, and traces. And if you think about it, then you need to implement this in a lot of languages. So it's like, okay, now it's like, this is super overwhelming. The good part is that OpenTelemetry said, hey, or this super clever guy said, okay, let's establish a protocol so we don't care about what happens in these tools and we have interoperability. So the protocol helps to abstract that. And okay, I don't care which language you are programming your tool or mine, they just talk each other. And also it unifies in the protocol metrics, logs, and traces, so you don't need a separate protocol for each of them, which is pretty convenient. And it also provides instrumentation libraries and auto-instrumentation for the code, so you don't need to think about it or put a lot of different libraries when you go to the code. So what is this thing about instrumentation? Let's start with zero code because it's fancy. So it's something that tells you effortless, helps you to create metrics, logs, and traces in your code, which looks super cool and it's great for your managers and because then you don't need to spend money doing things, but it has some inconveniences as well, as we will see. It's agent-driven. This means that, just imagine you are in Kubernetes, you will have an operator that will inject or activate some observability signals and in your code. And how is it done? It's done in 3 different mechanisms mostly, which is monkey patching or bytecode manipulations if we are talking about Java, or eBPF, right? Like I'm calling the kernel, there is an event in the kernel, and then I say, haha, you want to send a message, then I produce this metric or this span. But there are 2 super interesting calls later, talks later today about these topics, so I will let them talk more about that. I will be focused more on manual instrumentation. However, if you are curious about how this monkey patching works, for example, you can look at Wikipedia, super simple. Just imagine you are using this, this is an example before AI. Just imagine you are using a Python library and you want to say, hey, what's the number pi, right? Like 3.14. But then what you can do is, okay, at runtime, I change the behavior of this library. So at runtime, I change the value, and now it's like 3.2, the same as it happens with ChatGPT, by the way. But then it doesn't change the library itself. So OpenTelemetry, or these mechanisms, help you to, you have your library that is behaving in one way, but also you can, at runtime, change the behavior, so it starts sending metrics, logs, and traces. So that's the principle. And you do it by configuring libraries and exporters. For example, I want to generate metrics and send them to this endpoint. I want to generate, so this is what you will be doing when you do zero-code instrumentation. So there's nothing super fancy for the user, so it's pretty convenient. And it's great for edges and libraries. What I mean by this is you have your code, you would be, for example, calling your database, and you want to understand what's going on there. So the guys, super clever, of that database, they created some instrumentation for you, so you can activate or deactivate, so you can understand if you have issues in your code or in the database communication itself. So this is super good, but at the end of the day, not every language supports that. I come from the C++ world, and this doesn't work there. And it's also really hard to control the data, because you can, and if you don't treat it properly, then you can have a lot of increasing costs. And at the end of the day, we want to understand what's going on in our code. We want to understand if it's failing because of us, and you need to do something. So let's talk about manual instrumentation. That's why we are here. So when you start to include your OpenTelemetry libraries inside your code base, it's kind of hard. So actually, there was this survey a couple of months ago, or a month ago, that people were asking the community, hey, we need more examples. We need the documentation to be more thorough. So actually, this is a bit why this talk is, because when I was using to instrument my code, I was using OpenTelemetry, I had some doubts. So the first thing you need to understand, so now this is what we are going to talk about, how is this structured, how you can do it. The cool thing, as every other library, it provides an API and an SDK. So the cool part is that it's decoupled, so you can abstract yourself from, hey, where I'm sending my data. I don't care in my code, right? When I am processing my request, I don't really care where I'm sending my metrics, where I just want to don't pollute my code. So this is one of the principles. I have my API in which I say, hey, this is my +1 to this metric, but I don't care about the rest. And then you have the SDK. So let's start discussing how you do this for metrics, and we will also do it for traces and logs. For metrics, as I was saying, you normally have your function in which you want to add an error. So at the end of the day, what you want to do is say, okay, I have one more error, and then I don't care, I just throw it, and someone else will pick it up. So you do this by calling your API, and when you start reading the documentation, it can be, as every documentation, it can be boring, and that's why I'm trying to put here some fancy pictures. Maybe it's more clear. So you have these concepts that are measurements, instruments, meter provider, and yeah, okay, but I would just want to do like plus my metric, right? My measurement. And then you also have the SDK, which provides you a reader and an exporter, and what is that? So this is what I'm trying to explain now. So they tell me, okay, we have a meter provider. When I want to create a measurement, I need to call a meter provider, and a meter provider is this thing that will give me a meter. And what is a meter? So it's my interface, the meter provider. The meter is something that tells me which resource is generating the metrics. So it's bound, for example, to a library, right? In this case, if I'm using a MongoDB library, it will be a meter with this name, right? And then I can ask for this meter for an instrument. And what is an instrument? In metrics, you can have different set of kinds of metrics or instruments, so a counter or a histogram, so that's a meter. So then I'm done, because now I have my counter, right, my instrument, and I can tell, okay, I have one more error, and I push it, right? So we are now done with our goal. We know how to say, okay, give me one more error, or I want to report that I had an error. Well, we just need one more thing, which is if we go just to real code, what you will be having is you create, well, this is C++, of course, so lines can get long, but you create a set of labels, hopefully with no high cardinality, and you will say, okay, this ID or this response code, and I add it to my labels, to my metric. And I also, the number, I just said, okay, I just had one more, but you can put 10, right? So this is it. Right? So now these concepts come in again. I have a measurement, which is what I want to add, and I add it to an instrument, which is my counter. And then the other things are for the API. So that's cool. But what happens after that? Because I was wondering, like, okay, I just throw this metric, and now what, right? Well, it gets stored, into an aggregation store or into a local storage. And then the cool thing, and this is what I love about this project, is that it says, okay, now you define a reader and an exporter. So from this reader, you are able to say, okay, every second, every 5 seconds, every half a second, you say, now you get this data, you aggregate it, and you send it out. Where? In this case, okay, to an OpenTelemetry collector, but wait for it, because you can put another reader and say, you know what, leave these metrics here, because a Prometheus guy will come and take them. So now, I don't really care if in my code, if I decided that I will use a Prometheus, or if I will use OpenTelemetry forever or whatever, because now I'm done. And how you define this? You define this, for example, in a separate file or part in your code. You will be doing a singleton or whatever, and this is how you do it. So super quick. Here I'm showing you how would you define a reader. Like this, every second you get the metrics and you take them out. You will have define some parameters that you can do via configuration files. For example, hey, I have my OpenTelemetry collector or my backend there, so you define the exporter. So this is like configuration file, and yeah, a lot of code and to make things work. So it's singletons and stuff. But that's it, right? So. And of course, this one was an example for the OpenTelemetry exporter, but you will have the similar function for Prometheus if you want both in my example. So this is it, right? I have a measurement, I will throw it to my instrument, and that's part of the API, and then they will be stored and sent wherever I want, period, I'm done. So now we know how to instrument our code with OpenTelemetry in C++. Well, no. It's not only C++, because the cool thing about OpenTelemetry is that it gives you this. It's a specification for every language. So every language that implements OpenTelemetry libraries need to do this. Of course, you will have nuances, but that's it. So now you know how to instrument in every language in the world. This is pretty cool. Now, traces. We are done with metrics. Let's go with traces. Normally, what I see is that everybody thinks they know traces, but then they have some misconceptions. So if you allow me, I will do a super quick introduction to traces, because normally what I see is people thinking, no, this is just a low-level log debug, and then I'm done. Well, no, it's a different thing, at least in this notation. So what is a trace? Bear with me for a second. It's just some spans I put together under a trace ID. Nothing else, nothing fancy. Spans under the same trace ID. And what is a span? It's a representation of an operation. And it has, because every operation happens in time, I have this time dimension, which is pretty cool, because it will help me in the end. So, and why are these important? Because when I have a distributed system, and a guy is doing some stuff in JavaScript that goes to a Go API, and then goes to my database, and then something fails, then I cannot save my day by doing kubectl logs, because then you are like, okay, what do I do with all of this, right? So if you have a span, you can track. If you have trace, you can track. You can trace your call, and with these spans, like, okay, this service called this function, that's a span, and then I have this other function, that's another span, and then I have all the context. So this is distributed tracing, okay? And at the end of the day, as I was saying, yeah, you can check it in a Gantt chart, which is the normal visualization. Now, let's get to instrumenting part. Now we are more experts, so maybe we don't need to go deep dive into all of them, but This is even simpler. So I started, spoiler alert, I started with the most difficult one. Now tracing is even simpler because there are no different instruments. I was saying, okay, you have metric counters or histograms, they are different. No, here we have a span. There's no different sets of span. You have a span and that's it. So our API gives us a trace provider, a tracer, and the span. So I will be reporting spans, and they will go to the SDK to export data. So it's the same kind of representation. And let's start from the end this time. It's just, okay, I will be defining my resource. This is an important concept in OpenTelemetry because I tell, hey, this instrumentation or this signaling is coming from this resource, in this case my library or my program, so I have that. So at the end when I want to check the data, I can understand where this is coming from. So I put my resource, I also say where I want to export my data, like okay, I have an OpenTelemetry collector running there, and some options like batching, for example. I have processors, I can process my data, so I can check, okay, I can say, let's send it every megabyte. I don't want to have a lot of signaling, right? Another thing so that's for the SDK. Another thing I want to recommend, mostly in C++, because how it works, is to create this kind of auxiliary function that will help you to create child spans. Because what we want to do is to propagate context. Don't forget that. So I want to have a function in which I say, okay, create me a span out of this one. So it's just propagating the context, nothing fancy, but it will help you because when you are in the real world and you say, okay, I'm going to send an HTTP request. Okay, this is our example. Let's go with that. I want to send an HTTP request. So, hey, let's start my span, and I will set some attributes. Which attributes? How do you decide how to call these attributes? How are they going to function in the end? Well, that's a great question because the OpenTelemetry project defines what they are called semantic conventions. And there is a semantic convention for a lot of things. As you can say, I don't know, like for CI/CD or function as a service, or for example, HTTP, which is our case. So by using the OpenTelemetry library, you will have all these things already in your code. Because you know, okay, I am sending a request that is going to this URL. How do I put this in a span so I can check it in the end, so it's so easy? Okay, you just use this. You just add it to the span. You just use the primitives from the library, and you're done. You don't need to overthink or redo. So it's pretty cool. After that, so I added my URL to my span. I send my request, and what I do now is say, okay, my counter. Remember, we had our counter. Okay, +1. I sent a request, so that's another counter. It's not an error. And I add an event, which is another very important concept for traces and spans. It's not only about having this one called this one. No, you can add your logs. We all love to say, hey, I was here. Hey, this failed. Hey, I don't like this. If I am here, we are all screwed, right? These kind of things, we want to add them. So these are events in this jargon. And yeah, so, okay, I send this is just continuing with the example. I send my request. When I get my response, I will be adding another event. Hey, I will show you now in a super short demo. But then I can also validate my answer. And if it went bad, I can also add another event or set my span as this span was an error. So I can check in the end the trace. And we are done. However, we just need one more thing. If you are wondering how the hell this propagates, well, because you need to propagate the context. The service at the other side needs to understand your span and your library and things. So how does this travel? It travels, for example, in HTTP, it travels via headers. So, but then you need to invent them. No, this is standardized. And actually, these are the headers, and you will use them, just to give you a hint. So the library will handle this for you. In C++, if you want to do it yourself, you know, like, it's super big and everything, but it's just a couple of functions that you will say. The concept is super simple. Is, hey, I have this request coming from HTTP. Please inject them in this span. Or I am sending a request. Okay, let's take from my context, from my, the library, the primitive, and put them into HTTP headers, and I'm done. So that's the only part we were left. Yeah, we can do this super quick. Just to show how, like, why is this important and how does it look like? I have here a client that is sending 100 requests per second to a dummy server. And so let's give it some time so it generates data. And here we go. And let's refresh. And at the end of the day, what I'm going to look is to some spans, you know, like a trace, and I can check on them. And why all of this that I was saying is important? Well, we have now, I know it's super small, but we have these spans, because what I'm doing in my client is I send a GET request, then I get the response. I send a PUT request, then I get the response, so I can check the behavior of this other service at the other side. So the cool thing is, because I was instrumenting my spans with these OpenTelemetry standards and libraries, now I can inspect my span, and I can check here that, okay, this span corresponds to a POST method, and it received a 200 code, so everything is okay. Jose, you don't need to worry about these things. It was in OTLP format, it was a client. You remember I was saying this resource, okay, I said client, now I have here a client. I know this span is coming from a client, and also the URL I was calling was this one, and I can also have some information about the library that is generating this, so I can see that. And the other cool part is I have here my logs, right? So I was talking about metrics, logs, and traces. Traces, when you start using them and understanding its power, maybe you start to put less logs to the pipeline. And in case you were wondering, for metrics, yeah, now we have them. This is, by the way, I was just sending these metrics and traces to an OpenTelemetry collector, and of course, storing them in Jagger, and here in a Victoria Metrics instance. And here, you know, this is OpenTelemetry. In case you are not used to OpenTelemetry and more to Prometheus, you can visualize it the same. So you don't need to, for the user, at least this is not an issue, right? So you can easily take that. So that's it for the demo. Let me go super quick to logs, and we are done. Yeah, and in case the demo didn't work, I had those screenshots. Logs. You all know logs. That's the first thing we do as programmers. Hello world, that's a log, that's observability, right? We are all experts in observability and logging. So what I am proposing you here, right, is use, well, me, everyone, is metrics, logs, and traces with OpenTelemetry library, and that's it. Why? After all, you will tell me, yeah, but I like to just print to the console, yeah, whatever. We all do it. Actually, if you go to the OpenTelemetry library, they have, in their examples, they are printing to the console as well. So why shouldn't I? Well, if you continue doing this, first of all, you have already the library. You are using it for metrics and traces. So why not for logs? You can add attributes, for example, in an OpenTelemetry collector, if you use it to collect the logs. You can add the attributes, which are standardized, like, hey, this is coming from this container or this namespace. And you can also filter and batch, so you don't have a lot of signaling. You can transform and process the data, so it's pretty convenient. You can also help for correlation. For example, logs, if you add a trace ID, can you imagine how cool is that? Because now, because you like to look logs, okay, and you do your kubectl logs, if you see a span ID, now I can go to Jagger and check, okay, this is all the context. Cool, right? So there are many reasons why you should be doing this. Also, yeah, we all love, or for example, in C++, when you are instrumenting logs, then you start to reinvent the wheel, because you start, how do I activate or deactivate the login? How do I reduce the login level? How do I, and then you start, we all have that coworker, or even inside ourselves, that likes to reinvent the wheel and create another library for this and all that, and things can get messy. In this way, we already have it. Why don't we use it? However, I know you guys will be still using it. I will still be doing that, and I will just, hey, I have an error. I just put it to the console, and I'm done. Okay, if that's your case, it's okay, because what means putting your errors to the console, it means that Where in Linux, it's a file, you are putting your logs into a file. So the OpenTelemetry collector can read them, process them, and do all these things, and send them. Of course, you will lose some things, like correlation. You cannot correlate an ID if you didn't instrument it with a span, but at least you get something out of it. So it's not that bad. And okay, you are experts now in this. You will be creating your resource and adding it to an exporter and the processors and all of that. So you already know how this works. It's the same for all ones. And this is how it looks. So it's not that bad. I mean, it's super quick. You just say, OK, give me my logger, and I log my data. However, what I would recommend is if you are using traces, let's add your span IDs, because now you can, at the end, correlate. So it's just a small thing. But, and this is the last part, why, how does it look like, right? We know, hey, error here, that's a log. This is a log in OpenTelemetry, okay? It has those resources, it has maybe some timestamps, which is good because at the end you like the timestamps, you want to add them, right? It also has all this information about my library that I was showing, so this is all standardized. So my only message here is like, watch out, because these things can be expensive. We love to put a lot of logs there, but we will have, as I was saying at the beginning, there is another talk on how good or bad is auto-instrumentation. The same goes for manual instrumentation, right? Normally, at least in my experience, one of the biggest issues we had in performance was because we were logging a lot, and we needed to reduce them. And also with costs, right? Okay, so as a summary, if I want to give you some takeaways, or I would like you to take some things home, try to mix both worlds, because automatic instrumentation is also nice, but now hopefully you know a bit how to do a manual one. OpenTelemetry will help you decoupling the SDK from the API, so you can abstract your business logic from where you are exporting data and changing the exporters in this case. And semantic conventions, don't forget them. They are super important because they help us to correlate all the data and understand what the hell is going on. And okay, if you still want to, print, then if you use a collector like the OpenTelemetry collector, it will help you to inject some data and enrich your data so you can have good observability in the end. So that's it, and now we are open for questions. Thank you.
Do we have any questions?
Was rough last night, right?
I had a question about using it in embedded settings. So I have an embedded Linux system that I want to apply OpenTelemetry to.
Sorry, I cannot hear. Let me.
Is the mic not working, or?
Maybe it's.
I have an embedded Linux system I want to apply OpenTelemetry to, but I'm worried about things like the aggregator. How long does it retain it across reboots and stuff?
Mm-hmm.
Have you tried using it outside of like a Kubernetes cluster before?
So you mean inside the code, like in the?
I'm just talking like instead of on a cloud somewhere, like doing it on an embedded device with a battery and limited resources. Mm-hmm. Do you know how OpenTelemetry will fare, or? Yeah, in terms of, so if I understand correctly, you want to use the OpenTelemetry API and you are seeing that it's aggregating data and maybe it has some performance. Just imagine, or what, in my experience, what I saw is that it's actually convenient to have that, because otherwise you will be sending, like all the signals one-to-one, and then you have like a lot of networking issues because you are having all that bandwidth. Of course, you will need to fine-tune in the end how these things are, but I haven't experienced any issue with these parameters. It's just more like, okay, really, I just send 1 second of aggregation and I'm done. Of course, if your process goes down, then you may lose some data, but maybe, yeah, when things explode, it's not easy to debug. That's true. That's a great question. Thanks.
In the upcoming profiling signal, will there be also automatic and manual instrumentation?
So if profiling signals will have automatic instrumentation, I'm not an expert in that field, so I will not lie to you. I believe yes.
because I believe it's done with eBPF, but I will shut up and, and maybe there are other talks later, so maybe they will help you with that one.
Is that it? Let me say thank you.
Thank you, guys.
So do we have the next speaker present?
I have questions.
Lorenzo Nicora and Hong Theo. Are either of you here?
That's fine. It's okay. You want to use this one? Okay. Well, I can use this one. I tend to move my hands, so this probably sounds good. So he can use this one.
Yeah. You use that.
No, I'm reinforcing this stereotype of Italian. Using hands by phone. Yeah. So let me just finish the setup. Yes. Oh, yeah. Of course. Of course. Yeah. Let me also set this. Plug. Yeah, it works. So this is okay, good. Let me put this on. It's now yellow. When you press the button, it's green, and then you can. Oh, okay. What is the button? I think it's this mute button. Oh, okay, great. Let me do something. Sorry. I do this on something because I know I will get more. Yeah, so if you have 5 minutes left, I will show you this. We should be in time. For the 5 minutes before. Yeah. For the video team, stay between the two black lines. That's where the camera can see you. Yeah. And you're just wandering off screen. Yes. Okay. Okay. Speaking. Oh, okay. Perfect. I don't think we can do this. It's probably better. Yeah, no, exactly. Oh, we can.
Okay, we're going to get started soon. And for those new to this room for today, during the session, please don't touch the table. So decide now if you want it up or down, because they make a lot of noise. During Q&A, unless you really have to leave, please remain seated so we keep it as calm as possible, so we can hear each other. So we're going to hear from, sorry, I need to read from my telephone, Lorenzo Nicora and Hong Theo about Apache Flink and Prometheus working together. And we're going to start in 2 minutes. Are we all ready?
Yeah, we can do that. Just ask the question now.
No, better.
And I think we're getting started.
Okay, brilliant. Can you hear me? Can you hear me? Brilliant. So just to sound check.
Testing. Can you hear me? Should be right.
Perfect. So thank you. So let's crack on. My name is Lorenzo. I'm a humble Flink contributor, while my friend here, Hong, is actually a proper Flink committer, okay, Apache Flink committer, and we both work for AWS, but we are not talking about AWS today. We are talking about Apache Flink and Prometheus as open source, okay? So no AWS services here. Asking a couple of questions just to understand the audience. The first question, I think I know the answer because we are in the observability track. How many of you are familiar with Prometheus? Okay, kind of expected, I would say. But how many of you are familiar with Flink? Okay, much fewer. Fine. We will explain very briefly what is Flink and what we are talking about. And today we are talking about Apache Flink and Prometheus together for observability use case, so you're definitely in the right track. Spoiler alert, we're not talking about observing Flink. That's a different story. It's a solved problem. We're not talking about that. So I'm actually handing over to Hong to explain what we are talking about.
Yeah, sure. Thanks, Lorenzo. So I think let's set the scene a little bit first, right? So I think main thing is like observability, right? What do you want to observe, the first thing? So most of the time we think about stuff like servers, right? So we have a server, a bunch of, or some compute instances that you want to monitor. Like earlier we were talking about tracing, we're talking about logging, right? You have a server, you want to monitor it. And standard, right? You have some form of dashboarding, some form of alerting, right? Prometheus and Grafana stack, standard, right? So most of the time this works. You know, why do you need, what's there? There's no problem to solve, right? But nowadays, we have lots of stuff, right? There's lots of other devices that you probably want to observe, and you probably want to think about how you're going to build a platform to look at these things. So just a couple of examples here, right? You have a bunch of devices that are at home, right? IoT devices, right? You have phones, you have phone applications that might have, you know, network connectivity issues, right? Sometimes the data is on, sometimes the data is off. You might have different kind of like vehicles around, right? You might have, let's say, delivery parcels that you might want to track, right? So observability, I don't know, satellites, for example, I don't know, like stuff that lose connection periodically, right? So stuff, basically, you have things with intermittent connectivity, you have dispersed devices, and most of the time you have many devices. You don't just have like, I guess you have a lot of servers as well, but most of the times you have probably a lot more devices, right? A lot of different types of device UIDs, and how are you going to observe this? Can we use the same stack? That's the question, right? We have a solved solution, you know. We are familiar with this interface. We know how to use PromQL. We have lots of, you know, skills within this stack. We're familiar with it. Can we reuse this? That's the question, right? And hopefully we can, but we're going to explore it a little bit. So that's the landscape we're talking about. Let's look at the easy one first, right? Observing servers, right? So we know most of the time, like, there are different ways of doing it, but like Prometheus offers 2 different ways. Like, let's talk about this one way first, right? So you can put in a Prometheus exporter, put in some form of endpoint. You have a scraper, right? Prometheus scrapes. And then you store in a time series DB. And then you set up your visualizing and alerting, right? Using PromQL to query, and then you set up your graphs. Simple, pull model, right? So Prometheus pulls from the data source that you want. But can you apply the same to IoT devices, right? Just do the same thing. Possible? Probably not, right? How are you going to set up a server? How are you going to set up an endpoint? How are you going to be able to kind of collect this data on a periodic manner? Intermittent, like you have intermittent network connectivity. What are you going to do? So what we do is like we use the push model of Prometheus, right? So there's Prometheus gateway. So what you do is then you would basically have those components, remote write using a particular API or protocol that we have, remote write protocol, and you write it into Prometheus, right? So this kind of, you probably, like, I guess, what's this custom component? I guess it depends on your system. So it's generic in a sense that because there are lots of different types of devices, right? So how do you monitor these things? Most of the time you want to sort of set up some integration from your device into something else. I mean, it's up to you. It doesn't matter. The point is that you're pushing from those devices into Prometheus. But what are the characteristics of this kind of problem space, right? So one of the characteristics is that most of the time your devices have small hardware. You don't want to kind of set up like a huge memory or huge CPU on your, for example, your home device. On your, like, I guess if you use up a lot of memory and space on your phone, that's not a good application, right? So the point is you probably want to keep it as light as possible, right? You want to send probably things as, like, I guess as frequently as possible in case some of the connection gets dropped, right? You never know that you drop some packets. So there are certain types of problems that are specific to this problem space. We'll explain more about it later and why maybe the current stack might not deal very well with it. So yeah, so let's see. So let's explore PromQL first, just a quick summary in case people. So you can do a lot of things in PromQL, right? So you have all your data in Prometheus, right? Then you can filter and you aggregate the series in real time. It's really, really powerful, right? The semantics you can do with it. You can do rate, you can do derivatives, right? Derivatives, sorry. And you can do, like, I guess, windowing as well. There's lots of powerful things you can do with Prometheus. But then there are a couple of limitations as well. So, like, a couple of things around joins. So enrichment is something that's pretty hard to set up. So for example, if you wanted to, let's say, send a record with limited amount of information, with little, like, let's say just a UUID of your device, and you then want to enrich it with extra information that you want to do join over in Prometheus. Like, that's not something that you probably can solve that, right? If you wanted to, you could, but then, you know, it gets complex very easily. The other one is maybe some form of custom derived metrics. Like, let's say you have some form of state machine, right, that you have in your device, and you want to use that as a join with another metric. So it's not that it's bad, that it works, right? It's just that in the specific use cases, it doesn't work. And when you have super high cardinality data, right, you have lots and lots of UIDs, what are you going to do with it, right? So most, like if you have, let's say, hundred thousands of devices or 50,000 devices, stuff like that, you start to hit the limit where you want to run like over a windowing over 100,000 cardinality, you hit into some problems. So slow performance on high cardinality data. So let's, I guess, go back to the IoT devices that we talked about. Just simplified diagram, right? On the left, you have some observe assets, just to simplify it, generify it, right? So something you want to observe, basically, right? The problem space we're looking at is high cardinality. We're looking at probably potentially millions of devices, high frequency. So some of these devices send lots and lots of data constantly, right? Maybe different standardization as well. Some of them send very frequently. Some of them send sometimes 1 second. How you standardize it? How do you make sure that you have the same type of data across it, right? And then a couple of things as well, like maybe they send repeated data, right? You get duplicates in case you drop some of them, right? So there's different types of problems. And then, just to summarize, sorry, here. So you must use the push model. We talked about that. Not must, but push model fits better. High cardinality is usually a common problem. High frequency, or different types of frequency as well. And usually you want to keep it like, send something super short string, right? So usually you don't have the context info. So for example, like on a device, you probably don't know the create date, the make, like you can add it, but then you would increase, there's a trade-off, right? So you can also reduce, and maybe the contextual info might change with time, right? You want to keep it live. So stuff like that. So if you just use the same stack, process on query, right? Then you run into the problems that we talked about. On high cardinality, you have an expensive operation, right? And you're doing that constantly every time you refresh the dashboard. Like, I guess you can cache and stuff like that, but the point is, like, in the end, you still have this expensive query, if you want a live data, that you have to run constantly every time when you refresh the dashboard. Another thing we talked about, enrichment as well. You probably can't enrich it as easily. You probably can. You can plug it into Grafana. There's a lot of different, Grafana is really powerful. But the point is, all your complexity on this side, right? So what can we do to simplify it, right? And help you to, for example, build up a more extensible, a more, can we shift it the other way? So that's where Flink can help you, right? So what you can do is that Flink can step in as a pre-processing engine because Flink has very powerful time semantics. It can handle lots of like it's built-in handling of time semantics. My colleague is going to explain it a little bit later. But basically, like, it can take in a time series data, it can process it for you, it can simplify it for you, and there's lots of, I guess, similar to PromQL, if you think about that, but you can do it in a large distributed scale. Right? You can run it across like distributed clusters. They can process a lot of data, and you can do it in a reliable way. You can, if your cluster goes down, you can replicate the data and produce the same results, right? So it's the kind of thing that can scale very well, and the kind of thing that can produce you consistent results, which is important when you want to look at like counting, for example, a simple count. You want to count the right number. You cannot count twice, right? So stuff like that. You can produce consistent results, pre-process it, generate your enriched or aggregated metrics, put it into Prometheus, and then your dashboard can just query those. So it's kind of like allowing you to shift, I guess, the complexity somewhere else. Is it possible? Of course there are trade-offs, which we'll talk about, but this is one potential solution that can help you. So I'll hand over to Lorenzo.
Yep, thank you. So let's talk about Flink, just very briefly, and specifically for this type of use case, not in general Flink. But for who is not familiar with Flink, what is Flink? This is actually from the Flink website, from the Apache Flink website. This is the definition. Let's go through it because this actually contains all the relevant key points of Flink. So Apache Flink is a framework and a distributed processing engine for stateful computation over unbounded and bounded data streams. So what does it mean? First of all, it's a framework. It's a framework that allows you to code. So you write code. Java, mainly. Let's say all the JVM languages. I'm saying Java for simplicity, but you can use any JVM language, or Python. JVM first, okay? So you can write code, and this is where the power is, because you can do super simple aggregation, count over a town window. That's super easy. You have very high-level primitives for that, but you can go down as much as you need. So you can really implement the business logic. You're writing code in Java or Python. It's also a distributed processing engine because it allows you to run it at scale in a distributed way, and it scales a lot, okay? And it's designed to be fast, to manage, to handle huge throughputs, huge. Is mainly designed for stateful computation. What is a stateful computation? Every time you need to, the application need to keep in mind something. A count is stateful because you need to keep the count. Keeping the count is not difficult. You have a variable in memory. What is difficult is doing it safely if the application stops and restarts. So if you just keep a variable, when you stop and restart, everything is lost. So this is the part that is complicated, and Flink provides guarantees on this. Checkpointing, save pointing are not going down in that, but this is out of the box with Flink. So it provides what is called exactly once internal state guarantees. So the count will never be messed up if the application crashes and restarts. This is guaranteed. I'm using the count as the simplest example, but it can be something much more complicated. For example, mini-state machines about the state of one device. You can have a state machine for each device, and this is state, okay? And Flink will handle this for you. And the last part, bounded and unbounded data stream. What is this? Probably is not so important for our use case because we are focusing on streaming, but actually something interesting in Flink is it generalizes batch as a subcase of streaming. So with the same API, you can actually implement a use case and run it on a batch of data. You have a file set. You run it, as you would do with Spark. Then you switch to a stream, and you run the same as streaming, running continuously. The API is the same. And the way Flink does it internally is because it really generalizes a bounded data set, a batch data set, as just a stream with bounds. Again, this last part is not so important for us today because we are talking about stream processing. So it's an engine that keeps running. Another very important thing about Flink is it has multiple connectors. Connector is a component in Flink that allow you to connect to an external system. So Flink can read from many, many systems. This is totally not exhaustive, okay? It's just a few samples of them, and write to many, many systems. Streams, messaging, but also bounded data set. You can read files. You can read from a database. Same thing for writing. And again, this is not exhaustive. Notice that Prometheus is not there, or you used not to be there. And I will get there in a minute. So let's go back to our use case. So what we are talking about, what Hong introduced it, we want to do something like this. So we have our observed assets. We ingest them. We don't care how you ingest. There are many, many tools for doing that. Different technology, we don't care. So you ingest them. And you have all the events, all the raw events from your devices. And we want to pre-process with Flink and then write directly to Prometheus that we consider like a time series DB. And then the rest is what you're actually familiar with. Actually, you need an additional component in the middle because you cannot push into Flink. Flink is an application. You cannot push into the application. You need to read. Flink need to read, need to pull the data from some source. And because you need to flow data in, you need to stream data in, the most appropriate transport, let's say for this kind of use case, is a stream storage. Like Kafka, for example. Kafka is probably the best fit. But also like Pulsar, you can use messaging, you can use services like Kinesis, streaming. Again, messaging will probably be fine, but usually with Flink, with stateful stream processing, a log semantic like Kafka is better because it allows you to keep guarantees and go back to some point and replay if needed. But anyhow, you need a component in the middle. So your ingestion layer has to ingest this data, whatever they are, and send them to Kafka or any other stream storage. And then you will have Flink consuming in real time with quite low latency from Kafka, do the processing, and then write directly to Prometheus. So, and what can you do with Flink effectively? Well, you can solve the problem that Hong was introducing because it's very easily with the Flink API, with the programming interface, to reduce cardinality because you can aggregate horizontally. And you can actually aggregate horizontally, not just by the dimension you already have, but because you can do enrichment, because you can easily look up an external database, for example, to look up for, as Hong was saying, the model, the maker of a device, the location, what is the owner of the device, so all data that you probably have in a database. With Flink, it's very easy to do it efficiently, not in a dumb way, just querying every time a database, looking up and adding additional dimension to your data. And these dimensions are actually necessary for doing a meaningful observation. And because you're adding dimension, it becomes easy to use this additional dimension to reduce cardinality, reduce the number of actual metrics, because maybe for some use cases you don't want to follow each car, each device alone. You actually want to aggregate them. And if you want, you can reduce them. Okay? You can reduce granularity. Granularity means frequency in this sense, because it's not uncommon that with this kind of devices, the frequency they send raw events is very high, because actually they're sending events not just for observability. They're sending events for other jobs. And they may send multiple times per second. And multiple samples per second is too much for observing, for a dashboard alerting. It's a lot. Of course, you can throw it to Prometheus, but it's a waste of resources. And of course, you can do filtering if you want, filtering out outliers, whatever, and you can very easily calculate derived metrics. And this derived metrics is not just, sum to other metrics. Of course, you can do it, and you can probably do it easily also in PromQL. But as we are saying, you can, for example, implement some simple state machines. So based on raw events, they're not necessarily metrics. They're coming from device. You can decide that that device was moving from this state to this other state and then back, because Flink is stateful. It will keep the state also if you stop and restart or if the application crashes. So you keep track of this, and then you emit the state periodically as a metric. Okay? Of course, you need to turn it into a number. We are talking about metrics, by the way, here, of course. But this is something you can do. It's very powerful. And you can put any logic there. It's programming logic. So the top three features are very useful to scale, because they simplify scaling. You reduce the number of samples you're sending to Prometheus. So because we are talking about tens of thousands, hundreds of thousands of devices, it's a lot. If they're sending, each is sending 1 metric per second, and probably each device is sending, 10 metrics or something like that, you very easily reach a huge number of cardinality and frequency. And doing the top one, you actually reduce the throughput to Prometheus. You can do some, you can reduce cardinality, not granularity, the other, up to you, really depends. The bottom one, enrichment and derived metrics, actually simplify analysis or make some analysis possible. As I was saying, for example, if you don't have the maker, if you don't have the location of the device, and maybe the device don't know the location, you know it because of an external process. You have it in a database, but the device don't know it. And the device is only sending you the ID. How can you analyze something that is happening in a room if you don't know, if you just know the ID of the device? Unless you do some form of enrichment. So actually, the bottom ones unlock some of the observability cases, unlock some cases that you cannot do elsewhere, otherwise. Sorry, just checking, we are in time. So let's look at the integration between Flink and Prometheus. So what we are talking about, just zooming it a bit, in our Flink application. This is a very simplified representation of a typical Flink application. So in a Flink application, you always have one or more sources that are connecting to the external system, Kafka in this case, or whatever. You have many connectors doing that. You do one or more transformations, whatever, what we described. And then you end up sending the data to one or more sinks. We are showing one here, but you can actually have more. We'll talk about that later. And our idea is you have your observative assets, you ingest it. We omitted in this picture Kafka in the middle. Then you have the application reading from Kafka, transforming, and syncing, in this case, directly with no intermediary to Prometheus using the push remote write Prometheus interface. Okay? So if you are familiar with Flink, I'm sure you have heard about the Flink Prometheus metric reporters. Okay? So you were maybe wondering, what is this guy talking about? It's a solved problem, it's already there. We're talking about something completely different, okay? the Prometheus, Flink Prometheus metric reporter is designed for observing Flink. It's designed for observing the application. It works perfect, works well. It's a solved problem. But you cannot use it, you cannot hack it to handle your data. And it will never scale. Because your Flink application, even if it's running at a huge scale, even if it's super complicated, will never have tens of thousands of metrics. And the exporter is not designed for that. It doesn't provide any guarantees. It is not designed to handle data. It's designed to observe Flink. So we are talking about something different. We are not talking about this. What we are talking about is that sync. We need a sync. So until recently, there was no Prometheus sync connector in Flink. You can implement your own if you want. Remote write protocol is well documented. The only thing is you have to do everything by yourself. Because there is no Prometheus client, you have to use HTTP, you have to serialize, you have to batch. If you try to send one sample at a time, Prometheus will just stop receiving data very, very soon. You will not be able to say. You need to do proper batching. You need to be sure that if you parallelize the write, you keep the samples of the same time series in the same parallel writer. Otherwise, Prometheus will start spitting them back because they are out of order. And other things like that. So it was possible, but was very clunky. While conversely, with the connector, it's just a Flink component. You just put it there, and you send the data. So this actually was released recently, in last November. It's actually a contribution. We contributed, the two of us and a couple of other colleagues contributed. This is part of the Apache Flink project, okay? It's nothing proprietary. It's part of the Apache Flink project. It does support with the recent version, the supported version of Flink, 119, 120. The API is the same for Flink 2. We have to test it, to be honest. It should work fine because the API is the same. But Flink 2 at the moment is kind of in flight. Soon it will be ready. But I'm sure we will test it. I'm not sure it will work. And this is just showing the documentation very briefly. We tested it because the goal was working at scale. So we tested up to, like the seller says, up to, but these are real numbers, 1 million events per second with 1 million events per second, 1 million metrics, a cardinality of 1 million. This is not the limit. We stopped there. We stopped there because we said, okay, this is probably enough. And it was working. And the Flink cluster we are using wasn't huge at all. Okay? Wasn't huge at all. We just stopped there, and frankly, I stopped there because I had to request an increase of the quota of managed Prometheus I had, and I said, okay, 1 million metric, 1 million event per second is probably good enough. Let's stop it, but I'm sure it's capable to go further. So there are actually some trade-off, of course. Nothing is a free lunch. So the first one is this solution requires coding. There is no code solution, and you need to write code. At the moment, it's only Java. We are not yet supporting the Flink Python interface. We'll probably get it soon. But usually, if you want to have big volumes and have a low latency, it's better Java. Again, I'm saying Java, JVM. Many people are using Kotlin, for example, or Scala. Scala is becoming less fashionable, but for different reasons. But you can use it, of course, with Flink. The other point is, well, you need to run a Flink job. So you need to set up a Flink cluster. You can run on Kubernetes. You can manage it. It's not crazy, brilliant. But you have to do something. Okay, or you can use a managed service. Wink, wink. But anyhow, you can run wherever you want. But you have to consider this, of course. And you have to consider whether your observability team has the skill. Or maybe you need to bring in someone with the skill. So actually handing over to Hank for the conclusion. I think we are in time.
Thanks, Lorenzo. So I think just to kind of summarize what we've covered, right? So the problem space we looked at, right, is like devices, lots and lots of devices, right? So we're at scale. We have lots of cardinality, you have high frequency, maybe like you might need to clean up your data a little bit. Like you might have like devices which only can send a small amount of context, right? That kind of problem space. And we still want to use the kind of stack that we're familiar with, right? We don't want to build a custom monitoring solution. We don't want to build a custom dashboarding and alerting solution, right? We want to use what we already have. You can use Flink to plug it in, basically, so you don't have to learn, the end users don't have to learn something new. You can use that, and Flink will be able to allow you to scale your things you're observing, right? So that you can still use the same solution with low latency, and you can, yeah. So it solves it for you basically. So I think another kind of Easter egg, a little bit of helpful thing that Flink can do, as Lorenzo mentioned, Flink connects to lots of things. The job we showed is very simple, linear, right? One source, one transform, one sink. That's not all we can do, right? So the point of Flink is that you can, like, one of the things is stream and batch unification, which we can talk about later if you're interested. But the idea is that you can produce data at high speed, and you can produce data like in the batch, and you can use the same job to do it. The idea, you can read out about it. It's a lot of things that it solves, but in this case, it gives, once you plug it in, you get lots of things for free, which is the point we're trying to say. So you can code, obviously you can code your own server and you can manage it, but using Flink plugs into a lot of things. So the connector we wrote, that's free. You don't have to implement the remote write protocol and everything. You don't have to manage the time semantics. You don't have to manage the checkpointing. Everything comes for free. And in fact, what you can do here is Flink can write into multiple sources. It can write the same data with consistency into multiple sources. So for example, a lot of people, they want to write it into this dashboarding solution for maybe a particular user group. But maybe they want to store it, like for example, on a data lake, right? Somewhere in long term, right? Where you don't have to, like, you can query over like 5 years, right? Without having issues. And what you can do is Flink can allow you to write it in both cases using the same job, using one distributed cluster, one job on the distributed cluster to write the same semantics and the same logic into both of these things. When you update the logic of your job, both of the logic changes at the same time. Of course, there's coupling and stuff, there's trade-offs that you can talk about, but the point is, it simplifies all your logic into one, so you don't have to worry about like diverging data analytics platforms, which is a mess sometimes when people start building it incrementally. So the thing is, and Flink scales, so you don't have to worry about that and you can migrate. So I think another thing to mention as well is it handles multiple types of formats. So if you wanted to write into data lake with a different format that you write into Prometheus, for example, you can write in the columnar format, up to you. You can do it. Flink can handle it for you, and you don't have to worry about it. So yeah, so hopefully that's convinced you a little bit about what one potential solution you can try.
Yeah, just a couple of resources. We have shared the slides. So the first one is the documentation. It's actually part of the Flink documentation, so you don't have to search. It's the connector documentation. The second one is a GitHub repo with an example of the use case we described. Of course, it's synthetic. We have a data generator, and the data generator is simulating connected vehicles, sending the frame metrics. And well, you can set up everything, and you can run with tens of thousands of vehicles. It's actually another Flink application generating the data, and you can see how it works. And also, we have a separate application just writing the raw data as they are in Prometheus. So you can play with the dashboard to see how it is getting something useful from the aggregate and enriched metrics, and try to do the same with the raw metrics. Raw metrics are simple, but kind of realistic, okay? So you can play with it. It's a GitHub repo. And that is it. Please get in touch if you have any question. If you have any question here, we are here.
Any question? We have one question. Please remain seated unless you absolutely have to leave, so we can all hear the question and answers.
In case I hand over.
Yeah, that's fine.
Hi. The enrichment use case is really nice. But for the cardinality reduction and the granularity reduction, Prometheus already supports, let's say, 2 million metrics per series. Now you've added a Kafka there, you added a Flink cluster there, so I'm now adding more nodes, more machines. So can you share some cost analysis, like, okay, I'm reducing 2 million, how much more nodes I have to add in order to get the reduction?
Absolutely. I think it really depends on the use case, to be honest. So if you just do cardinality reduction, frequency reduction, it might be an overkill. The thing is, sometimes you cannot do cardinality reduction because you don't have the additional dimensions. So I think the key feature is enrichment, to add relevant dimension. And then it will allow you to reduce the others. The other thing it might be, well, you need to scale Prometheus. But I reckon if it's just that, you can probably do with Prometheus. The reality is what we have seen is most of the time you also need to have additional information, dimension that you don't have. Because the device is just sending the ID and the metrics and the measurement, or an event, raw event. These have happened, that's it. So you're absolutely right, we didn't do any proper.
Yeah, sure.
Sorry, a bit of an awkward situation. But yeah, just wanted to add to that. I think another thing that you're right, you're adding complexity right at the front. But why is it the right place to add complexity? Because, for example, if you write in something like Kafka, and you want to change the type of aggregation you want to run it on the exact same data over the last, I don't know, Kafka can store like, there's multiple tiers. You can store, so you want to run it over the last 1 year, and you want to change the way you analyze it. Flink can do that for you. You can read from Kafka 1 year ago, reprocess it, write into somewhere else. If you're using it, you can just plug and play, right? So the idea is that you can do it in multiple ways, but doing it here, like I guess people are trying to sell this idea a bit more because of that you can change the way you analyze. Analysis changes, right? You get new data on, I don't know, like 1 year down the road, and you're like, hey, you know, let me recut it a different way, right? This gives you flexibility. Yeah.
Hey, how's it going? Do you find that you've sort of pushed the problem back like further down with, I know, cardinality? Hello? Oh, there. Okay. Do you find that, you know, obviously cardinality explosions are very common in Prometheus, but do you find that it creates a sort of an overhead of maintaining those kind of rules and jobs like further down the stack, closer? You know, do you have a sort of a rule explosion then, you know, maintaining this huge rule set? Is that, I mean, I found that with recording rules in Prometheus, which is the way a lot of people tackle this kind of thing, that you just end up maintaining this massive rule set. So do you find that with the Flink jobs, or is that a thing?
Yeah. So if I understand the question correctly, so one problem we face when we do all this processing on Prometheus, which you can do like a rule set that you can kind of have derived metrics, but then after a while it starts exploding, right? You have lots and lots of rules, and you don't want to remove the rule because maybe something later on is going to use it, so you get huge list. So Flink, I guess you can end up in that situation, but I guess the difference is that maybe in Flink, like I guess you're accepting the fact that you're going to code something. I guess you can write it in SQL, you can write it in Python, you can write it in Java, but the thing is then you have the flexibility of not a config file. You have the flexibility of testing that code, you have the flexibility of integrating it with dummy data, assuming that and enforcing the interface, the data interface, that whenever you have this type of data, you're going to get this kind of results. So it allows you to have some, I guess it does add complexity, sorry, I'm not going to hide it. It is complexity, but it adds complexity in the right place, right, where you can then enforce against APIs, right? Then we talk about data contracts, we talk about different things. Flink is not the only solution. You can use like something like Spark, which maybe you're more familiar with, but we can talk about the differences between Spark and Flink later on as well. This batch versus streaming and stuff. Anyways.
And also, if you need to add rules, you need to add them somewhere. So either put them in PromQL or in Grafana Prometheus in different forms. I'm saying PromQL just to simplify, or you move it over there. Up to you. The good news is, well, in Flink you can unit test. Good luck unit testing what you do on this side.
Yeah. Talking about long-term storage, can you write directly? For long-term storage, can you write directly into a Thanos backend?
Directly into,
The question, sorry, because it's very noisy. You're asking about the long-term storage?
Yeah, long-term storage, and can you write directly into Thanos as opposed to going into a Prometheus and then going into a Thanos?
So sorry, it's really noisy.
I missed the last word. Write directly into
Thanos.
Oh, in Thanos. Yes, yes. Sorry. Well, effectively you are. Because the remote write interface is just an interface on top of whatever is the backend. So this was actually what we are doing. We were using, just for simplicity, the managed Prometheus that is actually based, I think it's based, I'm not sure what it's based on, but it's not just standalone Prometheus. So the answer is, of course you can. Of course you can. Keeping in a data lake is for different use cases. Because you keep it there, you do long-term analysis, you train machine learning, you do whatever you need, but it's parallel. So your dashboard is fed by Prometheus, you know how to do it, you have the other data.
Hi, thank you for the talk. You mentioned that the Prometheus sync implemented the remote write version 1. Are you planning to also implement the support for the remote write version 2, which was introduced with Prometheus 3.0?
Oh, we are planning as soon as it will be stable and released.
I think it's declared stable. Like, we'll probably hear the next talk, but
it is okay.
I remember it's already declared stable.
That's good. We will keep it updated.
Thank you. Yeah. All right. Thanks a lot for the talk.
There's a lot of people who want to see this talk. So we're going to need to move together in the middle. We need to compact ourselves.
It's about 10 Minuten, 20 Minuten walk from here. Hey, grüß dich, lange nicht gesehen. Wie geht's dir so? We can open it. We will
Wait,
check it.
we need to check seats. We need to check seats. You have the mic? So there's a lot of people who want to see this talk. It's not working? Hello? Hello? Is it working? No? Hello? No? Working. Hello? It was. It does? Yeah. Yes. Yes. So we're going to get started in 1 minute. And while during the talk and the Q&A, please do not touch the tables. They make a lot of sound. During the Q&A, please remain seated unless you absolutely have to leave. If you have to leave, do it very quietly. So the next talk is going to be from Brian Borum and Jan Fajerski about Prometheus 3.0. So please get started.
On now. Okay. Hello. Morning. Welcome. Stop moving tables. My name is Brian Borum. I am a Prometheus maintainer. I've worked on the code for about 7 years, and my day job is at Grafana Labs.
Hi, I'm Jan. I guess I can call myself a team member now too.
Yeah.
The PR is still open, so go vote for it. Sorry. Do I need to repeat? All right. My day work, I work for Red Hat on the OpenShift monitoring, and the rest of the time I try to contribute to Prometheus.
All right. So who's here? Who's heard of Prometheus? Okay, that's good. That's good. Who uses Prometheus? Everybody nearly. Who uses Prometheus 3? Maybe 5%. Is it okay? You can come down and report your bugs. So is anyone like totally new to Prometheus in the room? Nobody's owning up to that. Okay. So we don't need to go through the architecture. So that's good. That's going to save some time. I did want to put this, the QR code takes you to the documentary produced, which is really nicely produced and edited and so on, really high quality video. And it has the history of Prometheus. So I recommend that if you've never seen it. Yeah, I mean, the point of the architecture, Prometheus is a one process solution. And there's a lot of other things out there, and someone was just saying a few minutes ago you could add Kafka and stuff like that. So the big thing about Prometheus, it's you just run it, one thing, it runs. It does your monitoring and your alerting. So that's the kind of the key part of the architecture to stress.
Right. So not everybody has to go out and watch that documentary now. We have a little bit of history here. So Prometheus started at SoundCloud. It's over 12 years ago now. Yeah. As you can see, after the initial commit, there was like around the 2.0 release, and when I say around, like I'm talking years, right? It joined the CNCF, but also graduated the CNCF as the second project ever in each categories. And after that, there was a lot of focus on stability. There's long-term support versions now, and of course, now we have a 3.0 since November last year. Yeah, I think that's it for a quick one. Right, the new release. Obviously, there's a lot of stuff in there. You know, you have the cornerstones there. Obviously, we won't ever be able to talk about all of those in a single talk. Like some of these are a single talk. In fact, there are talks out there already. This is just takes you to a YouTube query that has the current Prometheus 3 talks. This will update over time, of course, which is nice. So today we'll pick out a few of these, and we actually look at some of what we consider breaking changes. Of course, with a major release, we can finally release some breaking changes, which is nice after 7 years. If you're interested in how to migrate, we have a very nice migration guide there that should help you out with everything, and if not, let us know. And I guess with that, we can start on the actual talk.
Right. So we're going to go through a few of the changes. So there was a change to regex handling, which is certainly one of the most memorable ones for me. So yeah, what does that do? Everyone uses Prometheus, so you should all know what this does. So I'll give you multiple choice. So it effectively doesn't do anything, is choice A. Who thinks that? It's a trick question. Who thinks it goes through every possible value, carefully checking each one? Actually, no, nobody thinks that. There's no option C, by the way. So prior to 3.0, it was option B. So it's completely obvious that it shouldn't do any work because .star matches everything. But, surprise, the Go code that was used to implement regexps, the dot does not match a new line. So every time you ran one of these queries, it would scan every possible value to see if it had any new lines in it. And you would not see those. Well, nobody has it. Like, hands up who's got new lines in their labels. Right. Right. So this was just a stupid mistake. But Prometheus culturally is passionate about breaking changes, about compatibility. So we did not fix this bug until a major version. So that's for me, that's the most memorable thing about 3.0, that once you decide to do a major version, we didn't do a major version just to fix this bug, but once you have decided, and we kind of decided it's about time, like 7 years, that seems like long enough for a major version. Once you've decided you can break things, well, the floodgates open. So we certainly fixed this one. I was very happy about that. And those kind of queries, if you have a lot of values, they go faster. So it's good. Okay, so there were a few breaking changes in 3.0. Luckily, they all fit on one slide. I
can read it.
We're not going to go through them. But yeah, just to give you some idea. So that's the release notes. That's a list of everything that was changed. Some of them are sort of fixing stupid things, and other ones were things that you could already make it work better with a feature flag, but you had to know that. You had to turn on the feature flag. And in 3.0, we basically turned on all the feature flags that you really should have been using, but we did not turn on for compatibility reasons. So yeah, that's the breaking change story. Let's move on to OpenTelemetry. We had a talk earlier. Some of you might have been in about OpenTelemetry. It's the big thing, the big standard for instrumentation. As of 3.0, Prometheus by default will accept metrics in the OpenTelemetry line protocol, OTLP format. So one of the big things about that is that the metrics are being pushed to Prometheus. Prometheus has always been a pull model, that it sits there pulling metrics in from wherever they come from. And OpenTelemetry is a push model, because I don't know. Well, I'm not going to be rude about OpenTelemetry.
Only got 30 minutes.
Yeah. That's going to take like an hour out of the talk. So anyway, it is a push model. So Prometheus now accepts metrics being pushed to it in OpenTelemetry format. So that's nice. One more from me. Yeah. So we decided to support all characters. That's why we refer to this as UTF-8. The one character that matters to OpenTelemetry is the dot, the full stop, the period. Label names in OpenTelemetry pretty much always have a dot in them. And Prometheus has always banned the use of the dot. And we thought, well, if we're going to allow one more character, let's just allow them all. So you can now write Chinese in your labels. You can write accented characters in the label names where they were previously restricted. But we do make you quote anything that is outside of the previous allowed set. So just put it in quotes like that example. That's in the migration guide, and there's a whole special page on what do we mean by UTF-8 support. So again, we threw open the floodgates. You can use any character. You can name your metrics after emoji. I did submit a talk to KubeCon called status equals poop, but it was not accepted.
That's a shame.
I'm doing one more. Why am I doing so much talking?
I don't know. I think I do this.
You do this one? Yeah, okay.
Right. So we're looking at another breaking change that was interesting. So we changed range selectors, or how they behave. In Prometheus 3, you have a left open interval. So yeah. No, sorry. Left close. Getting confused. So if you have a sample that coincides with the left border of your interval, you get that sample. That's can be surprising in a lot of ways, so we wanted to change it, make it left open, so that sample will not be included. And, we thought, it's a breaking change, but what can happen, right? The feature actually calls this impact mostly academic. Well, that's nice.
Because you have to get your timestamps really accurately aligned.
Correct.
To notice a difference.
In the migration guide, we're sort of a little bit more insightful. We explain this a little more. We do this. This might impact for some subquery use cases, some front ends that do certain things, but really mostly tests will be impacted, right? Easy peasy. Turns out, maybe we should show a query like this. So this is an example of such a subquery, right? If you don't know a subquery, this, where's my pointer? This down here makes it a subquery, so it takes the request total, looks back for 1 minute and gives you a range vector with 1 minute steps. So you can see already, I forced this aligning here, right? We have a 1 minute interval, but we only have 1 minute steps. So the second sample would fall right on this 1 minute border. And it turns out that these queries are actually more common than we thought they would be. So some people have problems now. But I want to use this query now to actually look at the new UI, because the new UI, besides looking much nicer, brings a really cool new feature, and that's the tree view and explain. So we have this query here, as I said, right? I wasn't lying. This doesn't return anything. In Prometheus 2, this would actually give you a graph, but we can fix it in Prometheus 3. We add 1 millisecond to the range query, and ta-da! Nice, right? But if we turn on the tree view now, we can actually look at what's happening. So the tree view gives you like all the components of this query, and you can actually select the individual components and get the results for that. So I selected the subquery here, and you can see, oh, we only get a single value at a timestamp. This is the old query, right, that now breaks. If we add that millisecond, ta-da, it's 2 samples, and the rate suddenly works. So that's really neat. I think that's the coolest feature of the new UI. I'm not a UI guy, as you can tell. There's more cool stuff, right? This actual explain tab also gives you really nice explanations when your query doesn't work. So here, you know, that's a different query, but basically we try to match something that doesn't match. We don't get any results. In the old world, you know, you had to like dissect your query and figure out, oh, where does this go wrong? This explain feature now tells you, oh, there's label sets that don't match. Fantastic.
We should give a shout out to Julius Volz.
Absolutely, who single-handedly implemented all this.
And his company Prom Labs. So if you want to buy any Prometheus training or consultancy,
reach out to him. Well, he'll show up in one more slide. I'll call it out. Right, the last one I wanted to show is this dreaded duplicate match group error, right? Who's here had that ever? Oh, not too many people, surprising. If you ever run into this, this can be a bit tricky to debug, but now with Explain, it'll tell you, because it has access to your data. It'll tell you actually the match group and where it has multiple samples, and you can go out and fix it. So how neat is that? That's for the new UI, or back over to you.
What went wrong? This is going to be exciting because I can't remember what's on the next slide. What did go wrong?
It's not too bad. Nothing.
Nothing went wrong. Well, no, so measuring what went wrong by what did we have to put out an emergency patch release for? Well, not much actually. There were only 3 bug fixes in 3.0.1. Nobody deploys 3.0.0, right? Always wait for the patch release. So the first one was actually introducing the thing that most people had problems with, which is the left open for subqueries. But we did want to make it consistent, and we didn't know it was going to. I personally had never seen one of those 1 minute : 1 minute queries until the bug reports came in. Like, why would you do that? Yeah, so there was a memory leak, and we had forgotten to support UTF-8 on one endpoint. But that was it. That was 3.0.1. Right. So now back to yourself.
Yeah. So with Prometheus 3, there was other stuff going on. Basically, somebody highlighted that somehow contributions are dropping. You know, it's not as active. Let's change that. So we want to make the Prometheus community more welcoming to new members. We want more contributors. And as part of that, there is actually a new governance document, I guess we call it, in the works. That's not ready yet, but look out for that. And now's the time to join Prometheus. At PromCon, actually, I showed a slide how sort of the contributions developed running up to 3.0, and now we can actually look at 3.0. So this is the contributions by contributor for any given release, right? We can see the release numbers there at the bottom. And I mean, looks pretty good, right? 3.0 was definitely a success in gaining new contributors and more contributions. This next graph there, this next not so bumpy one is, you know, Christmas, New Year's, everybody was off. And yeah, I mean, one contributor here sticks out a bit, right? But even without this person, this would still be quite a significant increase. And this is actually the UI edition here. So that was merged as one big lump. So that's Julius's work on the new UI. I said he would show up again. The same thing we can see, it's not just code, right? Not just new contributions, but reviews are really important. So this is from the DevStats, CNCF DevStats. You can look at review contributions. And what's that? Okay. I got to do this one-handed and in the wrong direction. Give me a sec. Shall I take the mic? Yes, please. Put this over here and put it in full screen. Woo. Okay, back to it. Oh, and the script is tiny. If you want to make that bigger, you can. Yeah, exactly. Reviews, very important to a project, right? If you don't want to contribute code, but you know, say, you know, an integration that we have in Prometheus for service discovery or so, you can review stuff. We like outside input and pointing out things that could be done better. So yeah, this also worked for 3.0. This the bump here is really sort of this year at the end. Again, we have a bit of a drop over the change of the years, but hopefully we can get that back up in the coming year. So yeah, that was really nice, and I think it's worth a round of applause for all the contributors who made 3.0 possible. So, call to action. I mean, you can join us. This is just picturing a PR. We just agreed to add 22 more people. Actually, we're doing two things. We're changing the governance so that there's maintainers and a steering committee, a very much smaller steering committee. So it used to be a bit of a problem adding people because it made voting harder. Because you had to get more and more people to agree. But because we're changing to have a steering committee, we can, we're very happy to add. There's just the people a little bit easier to read. So these are people who, a lot of them were instrumental in getting 3.0 out the door. And a number are just working away on some bit, maybe not Prometheus itself, maybe one of the exporters, something in the ecosystem. Anyway, these people have been working hard, and we are adding them to the Prometheus team. So we could have another round of applause for that, couldn't we? Congratulations to these people. All right, we'll let it open for questions now. If anyone has any. Yes. Do we need the? I think we repeat the question.
Oh, you could repeat the question. You could just shout. Yeah.
This is more of a joke, but when 4.0?
Oh, when is 4.0? Well, yeah, we have talked about that. We don't want to be another 7 years. We thought. Yeah, we sort of discussed, should we say that it's planned for 1 year, and then it'll probably take 2. Yeah, but not another 7 years. Yeah, quicker than that.
more questions? And if you can, please stay seated for 5 minutes, because if like everyone leaves, we won't understand the questions anymore.
You'll be answering questions. Oh, well, we can just don't talk too closely into this one. Yeah.
So, are there any changes planned, for example, for the open metric specification connecting to the Prometheus 3?
Are there any changes to the open metrics specification related to Prometheus 3? I think that's a no. So there is work underway to produce an open metrics 2. And maybe I should explain open metrics. So open metrics was an attempt to produce a standard which was not tied. People like avoiding vendor lock-in, right? That's a big thing. Nobody wants to be locked into a particular vendor. And in this world, Prometheus gets treated as a vendor, which is kind of nuts because there's no company behind it. There's no billionaires. You're not, right?
Not yet.
Not yet. No, you just got added to the team. So yeah, check in a week. So the open metrics was an older than OpenTelemetry attempt to make a standard. It wasn't as wide-ranging. It was just metrics, didn't do traces and logs, didn't catch on like OpenTelemetry did. So effectively, all the excitement is with OpenTelemetry, but OpenMetrics still exists as a standard, and there is now a group underway aiming to produce an update of that, which I think will be a 2.0.
Hi. Oftentimes, I have difficulty reasoning about, like writing unit tests I find it a bit challenging for Prometheus alerts. I was just wondering how we can use the new explain UI, or if you could throw the sample data to the explain UI that we throw to the unit test to help, make it easier to reason about the unit test itself. Like, can we combine the two things?
I'm not sure I get the question. I get it. I got the. So the question's about unit testing rules, like alerting rules.
Alert rules, yeah.
And you notice that there's cool new information in the UI. And could that information be used to help unit test your rules? Is that the question?
To make writing the unit test, like throwing the sample data at the unit test, make it easier to reason about unit tests and write.
Oh, you want to bring sample data from the UI into your testing rules?
Or the other way around. Like if I have sample data that I throw at the unit test, can I project them on the UI and see what my
you want to
test is
use
doing?
the UI to explain why your unit test is failing?
Yeah.
Ah, got it. Right.
Yeah, I mean, if you have a Prometheus on top of your unit test data, you can totally do that.
But it doesn't work. I mean, I think the context is PromTool, which has like canned data for rules, and I think I would count that as a good idea. So submit a feature request, please.
Or a PR.
Or just implement it. Yeah. We got one more up here, then we can come down here, I think.
Is gRPC planned for OTLP?
Is gRPC planned for OTLP?
Since you said you supported HTTP,
nobody knows.
No. I don't think at this point, but certainly not an expert. But maybe the expert is running now.
I think that's another one where we just need someone to do it. I don't think there's any philosophical objection to supporting gRPC for OTLP.
Is there any development on the agent mode of Prometheus? So if I want to have like multiple Prometheus instances that remote write to the same central Prometheus instance, there was this experimental agent mode, but it never really worked that way that I expected it to be. It still grew in memory like nothing. And I ended up using the OpenTelemetry collector instead.
So we did have a slide about performance. Is that there? Yeah. So your question was about agent mode, and we declared it stable, didn't we? It's no longer experimental, but it is not relatively any more performant than it was before. However, Prometheus 3, so these these charts kind of show that the CPU usage and memory usage of Prometheus 3 is better than like a couple of years earlier and way better than 2.0. Yeah, we did a lot of work on performance. It has got better basically with every release, but the agent mode is not like a svelte, lightweight speed demon.
So we got 2 more minutes. Are there more questions? No.
One over here.
One more.
While you're walking, let me say, please do try it out. We just released 3.1. 3.2
you could stay
is out.
seated for this last question.
Hi. Any plans to allow exporting OTLP directly? So if I have a data store, for example, that only accepts OTLP, that I don't need to translate it from remote write to?
There aren't any definitive plans. So we have, did we take the remote write 2 slides too? Yeah. So we have remote write 2 that sort of wasn't really a planned feature for 3, but it coincided with it. And that does allow to even think about this now. So it's way more structured. It can do the, you know better than I do where the issues were. But that would allow implementing this now.
Yeah, I mean, we looked at, so the question was about, are you going to implement OTLP writing from Prometheus? And I certainly find it hard to tell what's the difference in value between that and the OpenTelemetry collector. So if you can achieve what you need with the OpenTelemetry collector, which pastes in a whole bunch of Prometheus code, go do that. If you cannot achieve what you need to, please file an issue. And once again, yeah, join us. Please contribute. Make Prometheus a more wonderful thing in future. Thank you very much.
Thank you. Let's see if there you are, man.
So I nipped in on the edge even though I wasn't. Yeah, buddy.
I still remember your presentation from last year as one of the best that was. Oh, was it? So I'm super pumped last year.
I was worried, last year I was like, it's a little light on technical stuff. So.
But
this time I've just turned up with loads of them.
That was one of the reasons we picked you for. It's like you want to have at least one of those talks that are about the other problems as well. Like the technical problems is one thing, but if you want to get improving observability at an airline, so you're going to face the human problem and organization problem. They're going to outweigh the technical problem.
Yeah. There's some human stuff in there. It's a little bit more of a dive in. It's actually kind of. Oh, you're about to see it, so I won't spoil it. I was just practicing it and finishing it on Agent Theo. So. Yeah. Is it in the one in the US again?
Yeah, in Seattle. Amsterdam last year.
I should have come last year. You know what? I'm a bit wary of traveling to Europe right now. If I'm honest. I really want to come. I was actually tempted to do it, so I'm going to watch out for the next couple of days. The thing is that like last year, it's like family and Q2 now, so I've had enough of it.
I understand every second.
So like when she's like far now, like let's go to this thing, this place, and that place. Yeah, I really wish I had taken that. Yeah, I'm definitely.
Does that actually work?
Yeah, it does from the back, but you have to speak close to it.
Okay, so
every Q&A we have to remind people to speak close to it.
Okay.
But I was in the back of the room when Jan was talking, and I heard him when he put it away to. But you're gonna get a real mic.
And then it's on?
Yeah.
Nice. You've still got like 5 minutes to talk amongst yourselves.
I don't have questions. There's 60 slides, you're not going to have time for questions. You get to work out how to change slides, and that's 10 seconds going on each, isn't it?
Hi, can you hear me? Okay, cool. Hi, I'm Mana. I'm going to be your MC for the next couple of talks. And next up, we have James Belchamber and the performance impact of auto-instrumentation. And you can kick it up now.
Right, hey everybody. Yeah, I finished this about 10 minutes ago, so stick with me. Before I do, last year I did this thing where it was my first talk, so I did, hey FOSDEM, and I'm going to do it again because it was really fun, so hello FOSDEM! Woo! And that's the sort of energy that you've got after a whole day and a night. How many people were at Bite Night last night? A couple, okay, so it wasn't just me, awesome. And if I've got this much energy and you guys mostly weren't at Bite Night, then let's keep that up. Right, so hey everyone, my name's James. I've spent the last year or so in the trenches of an observability transformation. So I thought I'd come and tell you about it a little bit. So I'm an ops guy. I've spent about 20 years now working up from fixing computers door to door. I was a Linux sysadmin, then that became uncool, so I became a DevOps engineer. Now I'm a platform engineer, I guess. And so everything's coming from this sort of perspective. I'm now working with a great software developer who will be referenced in this talk a little bit as well, so we've got that as well on that side as well. You might know me from my talk last year, introducing observability to an airline, so I'm still there, still plugging away. Look at this guy. He was so young and so happy. So the stack that we built to support our auto-instrumentation needs has kind of evolved into a platform now, and with some pretty cool things since there. So we have collectors in our base images that are ready to export forward telemetry from to our back-end systems. We've got per-team customization on that as well. So we've got a nice suite of metrics that are coming from Node Exporter and Windows Exporter. We do have some Windows instances that we can use for systems monitoring. Notably, by the way, just as an aside, Node Exporter, if you're on AWS,
far better information than you're getting from AWS itself, so use that if you can. And we have everything as code as well, which is lovely, including our dashboards, which have key metrics that are vended and updated for all services based on what they're using and what we should be keeping an eye on, following sensible use, utilization, saturation, fine, and errors, and red, requests, errors, and duration, guidance for the infrastructure and application layers. Again, this is customizable on a per team basis. And of course, a lot of this is driven by auto-instrumentation. Am I allowed to swear? That's auto-instrumentation is fudging brilliant. Who here has contributed to the auto-instrumentation libraries? I was hoping. That's a shame. That's fair enough. These are cool, and wherever they are, I love them for doing this. This has made our job so much easier. They're basically there. You hate this when some people hate this when I say this, but it's basically like pattern matching. It reaches into applications. It recognizes common patterns, mostly functions in frameworks and like the standard libraries, and they write sensible spans to go with that code. So when you auto-instrument a web app, for example, you're not going to get everything. You're not going to get like your custom logic, but you're going to get the connection coming in. You're going to get the response going out. You're going to get like Spring Framework function calls. You're going to get database connections and stuff. You're going to see that all in your spans. It's a ridiculous uplift, and it's basically free. Basically free. Now, some people that I've worked with have pointed out that code needs to be executed, and that uses CPU cycles. These applications, which have been meticulously designed to be as performant as possible, mostly written in Java. So yeah, have you thought about the performance, James? And they're right. James, performance is impacted by auto-instrumentation. Luckily, this is something that I did some testing on. And so for this talk, I fleshed out my knowledge. I did some demos and stuff like this, and this is what I'm going to be sharing with you. So before we go deep, let's do some basic testing on a couple of languages that we can currently auto-instrument. I would like to say that this is not me showing you internal testing with a client. This is me using demonstrative testing that I can use to show what I've experienced. So the stuff that you're going to see up here is not benchmarking. You shouldn't be looking at what I'm showing you today as a benchmark of how these things perform. But it does help us tell the story of what I've experienced over the last 2 years. Let's start with Java. So Java auto-instrumentation is incredibly easy. If you've got Java in your stack at the moment, auto-instrument it. It's so easy. You download the agent, and attach the agent, -agent, and then you attach add two environment variables and restart the application. That's basically it. And like most of these solutions, what it's going to do is it's going to start pouring out OpenTelemetry protocol on 4318, I think by default, to localhost. And then if you want it to go somewhere else, then you can add another environment variable and stuff like that. And we, in this instance, we did want it to go somewhere else. So for all these testers, we're hosting the collector externally. That just means that you'll see a little bit more network traffic, but you shouldn't see any other performance impact from the collector. So to test auto-instrumentation, I wrote a very simple Spring Boot application. This is possibly my first Java application. And it just responds to any request on /hello with hello. Obviously, this isn't quite it. There is some other boilerplate. It is Java. I like Java, but you get the gist. So let's start with the most basic test. We're going to do a get, a sleep, a get, a sleep. So we're running 10 virtual users. We're running over 10 minutes, and we're just going to get my IP address on /hello and then sleep for a second. We won't do this often, but this is just like the demo. And this is what we're getting. So although it looks significant here, like this kind of stuff here, I want you to pay attention. I'll upload these as well. I'm probably run straight out of the camera, but it doesn't matter. You can see here like 5 milliseconds to 20 milliseconds on this. You can see these bars over here. This is all relative, but this is all within margin of errors. And so I'm just kind of showing this to you as an example of what we're doing. We can see the manual instrumentation at the top. This is average requests per second. This is the average P99, and then you've got your P99 in your requests. Errors don't come into it actually all that much, so I didn't really need that. That was probably a waste of space. And as you can see, we're not really seeing any difference between auto instrumentation, manual instrumentation. I asked Mania, who's the software person I'm working with, to manually instrument this Java app that I wrote as well. So we've got no instrumentation, auto instrumentation, and manual instrumentation. I also installed Node Exporter on the back end, so we can see 1 second sleeps. If you can't see these properly, I will upload them as well, don't worry. So everything hovers around the same place though, except for with memory. This is, what you're seeing here is, this is the weight of auto instrumentation on the RAM. Of course, we're loading this agent in, but these are on AWS, these are T3A micros, so these are 2 cores with 1 gigabyte of RAM. So, you know, there's not, again, relatively not that much going on here. And of course, you can see over in the network transmit there, we're seeing more, obviously, because we're sending out the spans, but pay attention, these are kilobits. So these are tiny changes. So essentially this is boring, and this was just me using it to show you like what we're doing today. So we're going to remove the sleep now, and we're just going to see what happens. So this is just your simple Spring Boot Hello World application, and as you can see, we've got something really weird going on. So manual instrumentation this is not margin of error. Manual instrumentation is performing weirdly a lot worse than auto instrumentation and none. So auto instrumentation and no instrumentation seem to be performing about the same, but we seem to be getting this ridiculous performance impact from manually instrumenting my little application. Let's pin that before you all crucify me. We will talk about that in a second. And again, looking at the instance stats, we're not seeing all that much going on. Again, weird. Manual instrumentation is using a whole lot more memory. But otherwise, this is just the story of a busy server. Let's pin that. Let's go and have a look at another language and see if we can get our bearings on this. Go auto instrumentation is also pretty easy. Technically, of course, it shouldn't be possible. The way that auto instrumentation works is it tends to attach to like a virtual machine or an interpreter, and it adds stuff. And how do you add stuff to a completely compiled application? Well, you use eBPF. eBPF is really cool. I'm not really going to talk about that too much here, but it's very much work in progress, this at the moment. I think they introduced a beta release. Is that true? Yeah, a couple of days ago. So do look at Go Auto Instrumentation. But again, you compile it. You do have to compile it currently. Upload it to your server. The way that it works is that it runs as a separate application, and it looks at the application you tell it to. Which is different. So again, Gin application. I asked Mania to write this again because I don't know Go. And we'll see how this performs. So again, sleep 1 second. We're not really seeing much. These are razor thin gaps. This is just margin of error. And with sleep 1 second on use, again, we're not seeing crazy amounts of differences between it. So let's go straight to the no sleep. That's the interesting bit. And this is more like what I would expect to see than when we saw with Java manual instrumentation, is that we would see actual, differences, sometimes significant, sometimes not. Again, this isn't crazy significant. In fact, it's the auto instrumentation that's performing the worst here. We're looking at 5 milliseconds versus 10 milliseconds. Like, that's not crazy big gaps. So yeah, we're seeing a significant drop-off in the requests per second as well. And again here, like, we're seeing server busy. We are again seeing auto instrumentation using more memory than manual instrumentation, but these are for relatively small differences. Okay, that was a lot of taking screenshots of Grafana and passing them off as slides. So let's go and look at some lessons that we can learn so far from this talk. So we definitely 100% know that they were right to suspect that code, upon being executed, does use resources. We also know that manual instrumentation uses resources. Okay, I'll get to the serious insights. One thing I didn't tell you is that Manya, being a great developer, is not a Java developer. Another thing that I didn't tell you is that we did this incredibly quickly. So we basically just got this application working and we just left it there and we started doing testing. Manya is a Go developer. So the manual instrumentation of our little Go application, although implemented just as quickly, was dripping with her previous experience. Like, you know, she knew how to write Go applications. And so this is the old adage, right? You know, it's like how assembly can be more performant than Python. And that's true, but can your assembly be more performant than your Python? We did actually go back and rewrite the Java code. And I did this mostly because I didn't want anyone that was working on that project to think that I'd misrepresented them. And as you can see, once we worked out what was going wrong, that we reran the tests, and now auto-instrumentation is performing about the same as manual instrumentation. But it was a great example of how manually instrumenting an application can catch you out, just like with any software development. This is the instance stats for posterity. Again, I'll put this in the slides that I'll upload in a bit. And you can see how now manual instrumentation is slotting in right between auto and none, which is the kind of thing we'd expect. So auto-instrumentation, by comparison, is much more consistent. You definitely can squeeze more performance out of manually instrumenting an application. But honestly, even if you can, at the expense of maybe getting caught out and bringing out bugs and stuff like that, it might not matter. What we might have built there was possibly one of the most simple applications that ever served a HTTP request. I'd wager that more resources were spent on creating and shipping a span for each request than actually serving the request itself. So what we've explored here is certainly interesting, and it's given us some basic orientation on the performance of auto-instrumentation. But I think it's time for us to start looking at the performance of real applications. I did say real applications, but I'm going to start with Pet Clinic. Pet Clinic is you've heard of Pet Clinic? I heard a couple of giggles, so yeah. Giggles, laughs, manly laughs. Pet Clinic is an example application written in Spring. It's a bit clunky, a bit slow. It has cute pets. I mean, it's basically a sample application that allows you to learn the tooling right. And it's kind of a pretend CRM system for vets. So we're going to instrument this. We're going to script some interactions this time. I'm not just going to do the one thing. I think I did like 17 different requests across the system. Searching, browsing, and form submissions. We'll see how we do. Now, the first thing I'll note is that I started with what I thought was a fairly lightweight test. But again, we've got this very simple server, and we've got this Java application that can't really handle, you know, that much. It's not designed to be performant. And 20 virtual users working through 17 different interactions, it struggled, as you can see. Errors bars started actually coming up here. So yeah, auto-instrumentation. I mean, is auto-instrumentation making a difference to this application? No. No, like 324 versus 326 requests. Like, this is, I mean, an application that's under a huge amount of load, but like, we're not seeing the kind of gaps that we were seeing before. But maybe that was just because I put it under a huge amount of load. The reality, and this is, by the way, the instance side, the only difference here really is in memory. It's worth saying that Pet Clinic uses an in-memory database, and I only gave it a gigabyte of RAM, so it didn't quite run out, but it was struggling. Let's lower the pressure on this, because let's be fair, even if this was a real CRM for vets, you'd have maybe 3 users making 5 requests a day. So, like, this is one virtual user, and this is our red testing. And even then, like, we were taking off the pressure. What you can see here is, and this is what I've seen in reality, you know, the measurable differences from our basic testing, from our performance testing, from our, you know, all of that stuff, they're gone here. You know, we're actually seeing that auto-instrumentation has very negligible impact. And again, on the back end, again, RAM seems to be the only thing I ever see with auto-instrumentation, a little bit more RAM. Again, we've got, that's like 60 megs, right? That's like a gig to play with. And so this brings us to lesson 6. An application that is actually doing something more significant than just serving a simple response on an endpoint is probably only going to be negligibly impacted by auto-instrumentation. Or really, indeed, manual instrumentation that's been done well. I'm going to go through a couple more, and then we'll move on. Let's pick something that's real, that's doing less. Did you know that there's a module you can add to HTTPD that starts pouring out spans? It's good. And of course, HTTPD is like a C++ application, so that's really cool. I don't know if it's auto-instrumentation. I guess it's no, it's just instrumentation. But I did one pass at this quickly. Turns out that I had to turn the errors. It's going to hit the just it works page. You know, you loaded up Apache HTTPD and does it works? That's a 403. Who knew? And yeah. Whew. So this is HTTPD just responding with the simple, you know, HTML page, it works. And as you can see that we're adding an order of magnitude more on top of that in terms of response times. And we can do three times the throughput without auto-instrumentation versus with auto-instrumentation. And at the back end, you know, the disk was much more aggressive. Interestingly, I think that I could do a lot of tuning here because I think that it was writing a bunch of logs that it didn't need to write. They weren't errors, that's just by default what it was putting there. And this only had 8 gigs of disk space. So I suspect there's tuning as possible. But this kind of represents the fact that you should really be thinking about what your applications are doing, because if you've got a HTTPD instance there that's just meant to be very quickly responding to like static requests, you know, that's an example of something where you might see an impact. But this is not how people use HTTPD, is it? People use HTTPD to host WordPress and then argue with each other. Let's put WordPress behind this and try again. You can see here that I ran WordPress with and without, I could have chosen Ben and labels for this, with and without HTTPD instrumented. And then I instrumented WordPress itself with PHP-based auto-instrumentation, the rare double auto. And as you can see, like here, like with the big gap that we saw between HTTPD being auto-instrumented and not auto-instrumented, that basically disappears here. And actually, it's the PHP-based auto-instrumentation that you start seeing having a problem. Not significant. I'd say that I'd still be happy with that, personally, because I think that it's worth it. We'll talk about that in a second. I'm not entirely sure what's happening here, but I will note that for each request to load the sample page on WordPress, it created 35 spans. 22 of those spans were database queries. This is for this single sample page. I don't understand WordPress. But yeah, otherwise everything looks pretty much within margin of error. And honestly, that's not, I've done WordPress hosting, and that's not what people worry about, right? When you're doing WordPress hosting, you're thinking about your caching efficiency. So again, you see that performance impact and you go, oh no, big performance impact. And then you think about your application. Well, actually, most of your WordPress applications, yep, 10 minutes, I'll speed up. Most of your WordPress applications come from caching, you know, you're looking at caching efficiency for your performance impact. But it does underline the need for good performance testing, which you should be doing anyway. But when someone asks me, what will the performance impact of auto-instrumentation be, my answer is well, test it. Because it does depend on your application. And most of these, you know, auto-instrumentation stuff, it's been pretty easy to instrument. So the harder ones with the HTTP module, had to spend a bit of time on that. And WordPress, because WordPress doesn't install with Composer, and the auto-instrumentation installs the Composer, but you'll work it out. But yeah, the little bits do add up. So yeah, get into performance testing your applications, and now is a great time to start. Okay, so far I've been relying on you, dear audience, to believe me when I say, hey, all of this is worth it. But I would like to label a little bit on why it's worth it. Firstly, looking at applications in terms of traces. Even if you have the most perfunctory span, and most of your application is just custom code, you're still going to get the request span, you're still going to get things like the database calls. This is actually an example that we had from a real application with our client. This isn't a real trace. Grafana Tempo doesn't output this. But this is a representation of the problem that we had. We had an application that had a huge amount of custom logic, and we were basically not seeing anything, even with auto-instrumentation. But we did know that one of the things that we were being told is that the application that we were running, that they had developed, was slow because our database wasn't performing as well. We were hosting the database, and our database wasn't performing well enough. And of course, databases never perform perfectly. So of course the database engineers went off and they tried improving the response times in the databases. And they could see that there were some slow queries and things like that. But from the traces we could see that when we got very long requests that were causing us problems, we were getting very short database queries. So we were able to flip the script on that problem and to be able to say, hey, yeah, we know that there are slow queries, but those slow queries are not connected to the slow requests in your application. And this was because it was a Java application, so we could just auto-instrument it. It was incredibly easy. The other thing is automated metrics. A lot of, especially older applications, aren't outputting the metrics that you need to be able to do proper red dashboards. And even if they do, they might be wrong. With auto-instrumentation, you can pull all of this out, and we could create dashboards that upper management had been asking maybe for years, and they were not being put ahead of, feature requests and stuff. It's very easy with tracing to go and generate metrics from that. There's also things like the service graph. I'll get through this very quickly. You've seen this in other things, but I never really understood the value of this because I was just like, well, it shows you how your application works, but you know that, right? But of course, with a lot of enterprises, going back to maybe 60s, 70s, 80s, 90s, they've got stuff that was developed, that was out-developed maybe 10, 20 years ago, and only very few people actually understand what's going on. And to stay understanding what's going on, they have to work very broadly instead of being able to get deep on stuff. Traces just give you this map of everything and correct everyone's understanding really, really quickly. And even when you've got applications that are not instrumented, where you can't auto-instrument and you're not able to go and manually instrument them, there was somebody in the last year that was doing COBOL. Does anyone here do COBOL this year? Yeah? Pointing at someone else. Are you grassing on them? Are you grassing on them for using COBOL? So yeah, there's no instrumentation library for COBOL, so far as I know. But you can inject the context for the trace into the application, which means that you can go, oh, it went off to this application. I can't see traces for that. But I can click a button and see all the log lines that match it. God, that's useful. And as we've seen from our experiments, the performance hit is not really apparent at the scale of whatever most applications are doing. You should be doing performance testing. But if you don't have any of the things that I just listed across your whole estate, you should be leaning towards auto-instrumentation. You should be leaning towards picking up these libraries, testing them on your systems, implementing them, and getting them out there, because there's not much of a reason not to. It's free observability, and it's so useful. I do want to talk about manual instrumentation for a moment, because you might be thinking that what I'm telling you here is don't do manual instrumentation, only do auto-instrumentation. It is true that manually instrumenting code is a ton of work. This, for example, is a simple application, and all the bits in yellow are bits that you need to do to instrument your application manually. Of course, this is unfair as an example because of the more complexity you have to your application, the more code versus other stuff that you need. So the balance would change. But this is still a ton of work, especially on instrumenting existing applications. Doing it for new code is really, really easy. You should just do it. Just start doing it. Just start. The other problem is that humans, of course, create bugs. They also fix bugs. They also create bugs. Auto-instrumentation has already been written. It's been tested in a lot of places already, and the bugs have been worked out to varying degrees. Some are more further along than others. And of course, because it's open source, you might find it easier to fix the few problems that you're having in your auto-instrumentation than you would in debugging your application and getting it working without manual instrumentation, which of course is the beauty of open source. And the other thing is that auto-instrumentation, you hate this slide, don't you? I've not found a better way of explaining it than this, frankly. The reality is auto-instrumentation is awesome. It's fudging awesome, but it's also reasonably dumb. It's essentially doing pattern matching under the hood. It's finding things and decorating them and stuff. Loads of people are going to come up to me afterwards and be like, it's not that, and correct me, please do. But it's guessing at what attributes should be and shouldn't be added, and of course that's not going to match your application. And so how well it works is going to depend on whether you're mostly writing custom logic and custom code, or whether you're mostly leveraging applications that have already been auto-instrumented. So it's kind of like the bus that you're going to get almost to your destination while you're still working on that custom rocket engine that's in your garage. The rocket car isn't ready yet, and the walk from the bus stop isn't that far. That sounded so much better when I wrote it down. And with auto-instrumentation, you can start your observability journey now instead of waiting. Remember, observability isn't tracing. Observability is a different way of working. Instead of your telemetry being something that you design and then instead of telemetry being something that you design in to answer known questions and then implement as part of your software development, telemetry becomes something that you implement to expose the internal state of the system. And then you can start asking questions of it outside of that loop. You really want to get to this for two reasons. One, it's going to be a bionic arm for your troubleshooting. But secondly, it means that everyone else has got this capability as well. They don't have to ask you what's going on in your application. They don't have to ask you to implement that new counter. You can just say, no. The traces are there. We've made sure that the attributes are all there, and just go and pick it out. Right, have I got time for miscellaneous? Okay, really quick. Okay, firstly, AWS Lambda. AWS Lambda works, so if you're using that, the only thing is that by default, the AWS version distribution of OpenTelemetry includes the collector in the Lambda layer. If anyone works on Lambdas, you'll know that one of the things you want to do is you want them to start up and complete very, very quickly, and having a whole collector start and then stop again adds a huge amount of weight to that. I would recommend adding an external collector and having it sent to an external collector again. Your mileage may vary, but this is something that's really important when it comes to performance of auto-instrumentation. The other thing is Grafana Baylor. Well, I'd say generally eBPF. eBPF is awesome. As we could see with Go, it was your only option. With C, C++, with Rust, it's going to be your only option for getting traces out. But it gets you less unless you configure it. That might change as we go on, but at the moment, if you use eBPF-based auto-instrumentation, it will give you less in the way of spans, it will give you less context. Someone will come up again afterwards and correct me on that, and I'd love to see it. But my experience is that it's giving you less, and also it's about as performant, maybe a little bit less sometimes, maybe a little bit more. So my approach is still to use traditional auto-instrumentation where you can use it, and to use eBPF where you can't. Again, I've got the, this is just for posterity, you'll see this afterwards. So yeah, these are our lessons. You should probably be using auto-instrumentation. Time is up. You should probably be using auto-instrumentation. So I'll just say at the end there, we are looking for people, community-led projects that want to leverage this kind of stuff. We've benefited a huge amount from this, so we want to give back. So if you're running a community-led project, open source project, come and talk to us. We'd be really happy to help out, because it helps us out with some experience as well. So
maybe we can give 1 minute if somebody has a question.
Is there any questions, or did I perfectly answer it? Oh, there you go.
Okay, thank you for the presentation. So in my experience, auto-instrumentation tends to create a huge volume of traces, metrics, logs, which in the end cause costs for the storage of those that are sometimes one order of magnitude higher than the cost of running the application itself. So how do you handle, like you should, what are the strategies to reduce the costs?
Okay, strategies for reducing cost. How much do I want people to hate me? Fuck it, don't use Datadog. So what we're using at the moment is we're using Grafana Tempo, not an ad, but it sends it straight to S3. So you get this, ability to do all the things you can do with S3 to store this stuff, and you can use any other backend as well. Storage of spans doesn't have to be expensive. I think that's just a choice that the industry made. But the other thing is, yeah, once you've gotten to the case where you're spending, we're just not spending that much. I think, you know, I'm not going to quote a number, but we're spending like 0.01x what we're spending on running the applications, and we're using auto-instrumentation. So, and all I can tell you is that the way that we've done that, the strategy was saving money by using a tool like Grafana Tempo, which pushes it to S3, which gives us those economies of S3 rather than the economies of maybe something like, you know, Datadog as an example. And very specifically, I do call out Datadog because many people have come to me and said, we love this idea, but we don't do it because it's so expensive, and I find out that the reason is that they're using Datadog. If you're listening, Datadog, lower your prices.
Thank you, James. I think that's it. We're
Your mic then.
This one is.
It's a bit silent.
Many people touched it.
Hello? Test.
We have the same problem.
Hello?
Is it working?
Covering up the tissue is really hard to find you guys. Is everything going smoothly? Not overcrowded, excellent. And you're the next speaker?
The MC.
There's the next speaker, okay, good luck.
when we switch between full and...
Okay, yeah, I'll give you a bit of...
Oh, you have...
So, do I get a chair or do you go down?
Oh, yeah.
Sorry.
All right.
Check if you're happy.
Awesome. Yeah, cool.
Yeah, I guess. He's doing the second part, so I will not run out of time. We're going to keep these things running there? Yeah, I will start it as well. It's never too much. I don't. No, I just here. For the video, we should stay between these two lines.
Okay, I think we're ready for the next talk. And we have now Fabian Staber and Rafael Roqueto with Zero Code Distributed Traces for any programming language.
I can take it. So, yeah, hello. Welcome to our talk on zero code distributed traces for any programming language with eBPF. So that's the topic. Few words about us. So I'm Fabian. I am engineering manager at Grafana, also active in open source, a contributor to Prometheus, and we have Rafael.
Does that work?
Oh.
Yeah. So I'm Rafael. I work at the Grafana Beta, software engineer. Also background in open source, mostly involved with the Qt project in the past. And yeah, here we are.
All right, and the way we structured this talk is I will do more the introduction, overview, and saying like what problems we are trying to solve, and then Rafael, as the actual engineer, will talk more about how we solved it, and he will do the main part of the talk, I think. So let's see. But for introduction, the tool we are going to use is named Grafana Beta. It's an eBPF-based auto-instrumentation tool. It's open source, it's on GitHub. It's currently under the Grafana GitHub organization, licensed under Apache 2.0 license. However, we have started a process to donate it to OpenTelemetry. It's currently being reviewed by the OpenTelemetry Technical Committee, and once this review process is done, our intention is to move it over to the OpenTelemetry project, within OpenTelemetry, it will likely not keep the name Baylor. It will be named something like OpenTelemetry eBPF instrumentation or something like that, right? So there's the ticket, like if you want to follow the status of that. Yeah, and I guess like what is Baylor? I mean, if you want to show a tool, like the best thing you can do is a demo, even if it's back-end tool, so there's probably not too much to demo. But what I did, I had implemented a couple of Go services running in a local Kubernetes cluster on my laptop, installed Baylor as a daemon set, told it to instrument everything in my default namespace in Kubernetes. It found these Go services, so there's a couple of them. And what we see here is a pretty standard, Grafana dashboard with the 3 most important metrics that you would like when you monitor HTTP services: request rates, error rates, and durations, how long things take, right? And so this is all metrics, right? This has nothing to do with tracing. But where tracing comes in is if you, for example, see that the error rate here of my product service is more than 20%, you might want to learn what's the reason for that, right? And in a distributed application, of course, the root cause might not be in the product service itself, but somewhere downstream, like whatever it's calling. And so this is where tracing comes in. So you go to your trace database, run a query. For example, you would say, I'm looking for any span within HTTP response status code of 500. Then you get examples of erroneous calls, right? And if you look at such a trace, so let's maybe close that window so that we have a little bit more space. So you see, as indicated by this red symbol here, that there is an error in the product service. But if you scroll down, you see that this product service also calls the pricing service a couple of times. And there's also an error down here, right? And so if you open the details, you can have a look and see that it's an HTTP request and which path is called and what. Now I cannot scroll down anymore, but I don't know. You get the picture, right? And so the reason why I'm showing you this is, to just let you know that this talk is about distributed tracing, and also the previous one, and there's a lot of talk about distributed tracing. Metrics are still, I think, the core, like the most important signal, right? Metrics are what you have on your dashboards, what you define your alerts with, what you use in your SLOs, and so forth. And metrics with eBPF works pretty great. So we have support for a lot of network protocols, HTTP, HTTPS, gRPC, HTTP2s, and so forth, right? Huge list. We are adding more and more to it. It works for any programming language. So I listed a few here, but actually, I think as of today, I'm not aware of any language where it doesn't work. So if you have any language where you wouldn't get proper metrics, open an issue, we will figure out why, but it's actually pretty stable. And of course, there's not only network metrics. We have process metrics, like whatever memory usage, CPU usage, and that stuff, right? So if we do tracing, I mean, because as you have seen, if you actually want to go to the root cause of things, tracing is pretty useful. Tracing with eBPF is harder than metrics with eBPF, right? So why is it hard? So basically, you need to do 3 things if you want to do tracing with eBPF. So we have a service here. It gets incoming HTTP requests, does something, and at some point performs an outgoing HTTP request, right? The first thing you need to do when an HTTP request is coming in, you need to figure out if it already is part of an existing trace, which you learn by looking at the HTTP headers. There's a trace header with the trace ID and the span, parent span ID. And this is done, right? We can look into headers of incoming requests and parse these and, figure out the current span context. The second part, the service does something, and you need to keep track, when the service does an outgoing request, which incoming request is the context that this belongs to. And this is, depending on the framework that you use, this is hard to do with eBPF. So we solved this for a couple of frameworks. First of all, if you have just a single-threaded application, that's easy, right? If you have the standard Java servlet model with 1 thread per request, that's also easy. If you have multi-threading, it gets harder. So we solved it for Go. So if you start a couple of Go routines and they are scheduled and so forth, we track these Go routines and can still know what the original context was. So multi-threading with Go works. We instrumented Node.js async loops and so forth. So there are a couple of frameworks where we reliably know which outgoing requests belong to which incoming requests. But we have to be honest, it doesn't work in all cases. So for example, if you have a fancy reactive Java application with some kind of framework where it's, there's a lot of scheduling back and forth on thread pools, we might lose track. So it basically depends a little bit on the framework that you use, whether we can track these requests or not, right? And then the last part is, if you figured out the trace context that belongs to this outgoing request, you need to add the trace ID and the parent span ID to the outgoing request so that the next service downstream knows which trace this request belongs to. And this is also hard to do, but this is something that we solved in the previous couple of months, and this is what this talk is about, right? And now I'm handing over to Raphael, who will tell you all the details, like what we did, what problems we ran into, and so forth.
Cool. Thanks, Fabian. All right. So, as Fabian just explained to you, what we want is to propagate the context. So this is the sequence diagram of the demo that Fabian just showed you. And we have all these requests going on. They are non-dashed arrows. And so what needs to go around? Basically two things, the span ID and the trace ID. As you know, span ID identifies each individual request, and the trace ID is used to tie them together. So we have one ID that chains everything together. So that's more or less what it looks like. We got header, HTTP header that gets injected. It's defined by the W3C. It's called trace parent. So it's made of the vendor info, the trace ID, the parent span ID, and the flags. And then we end up with this big string there that gets injected into the HTTP header. And how is that done? Like, how do we pass that around with auto-instrumentation or not? Like, how can we inject that? Well, the obvious way is to use an SDK, right? There's some pseudocode there, some API, and we do it, but, you promised us zero code instrumentation for any programming language, so that's not what we're going to be talking about. And that's where Bela comes into play with eBPF. Just being curious here, who's familiar with eBPF or knows what it is? Like being, okay, that's great. For those who don't know, in very, very, very constrained terms, it's a Linux kernel infrastructure that let us run really small programs. They are very safe. They go through a verifier. And these programs, they give us some kind of visibility inside the kernel. And we can attach them to different parts of the kernel. There are different kinds of eBPF programs that do different roles. And we use that to correlate the requests and also to inject a trace parent. So basically, we have two simple requirements to do that. One is correlating incoming requests, as I said, and writing memory. So writing trace parent header at that level, eBPF level, we're basically writing process memory. And that's where the problem begins. So it's kind of difficult to write process memory with eBPF. So, this is just verbose code. It's an example of how we do it with Go. We don't have to really understand it. The takeaway here is that eBPF programs, they don't have, you cannot use libc or anything like that. You can only use a set of predefined helpers. One of them is called BPF probe write user. And in this case, we're using this to inject the trace parent string for a Go application. But this helper, it's a bad idea. It was added back in 2016 to Linux kernel, but the main goal was just to help people messing with eBPF to make experiments or debug things. And because you're writing user space memory, you can crash your program or do bad things. And also you need capsysadmin, which means you need root. So security implications. And yeah, you will see this helper in a few auto-instrumentation projects like Bela, Hotel Go, but mostly in malicious codes, like if you go in GitHub. So because of that, it was locked down in August 2021 under the Linux security mode, meaning that for production, it's really difficult to use it. I mean, it's being used, it works, but you know, it has a lot of downsides. So we'll start looking for alternatives, like what can we do? Well, the eBPF probe write user, it works in one kind of eBPF program called probes that get attached to, it's like a breakpoint, making a very bad analogy, that it get attached to a function in your program or a kernel function. There's a different kind of program called a classifier program, BPF program I mean, that lets us see network packets. So it's no longer, we're not longer dealing with functions or kernel functions, but it sits really low level on the network stack, close to the, the data path, close to the network card or the, lowest level. And we can analyze the contents of packets. And these kind of programs, they let us change the contents of the packets, or write packet memory. So not program memory, not user space memory, but just messing with the packet. So here's the idea then, that what we're trying to do. We see all these packets going through on the egress path, so the outgoing packets, so that those are the outgoing HTTP requests that Fabian was talking about. We see if, okay, do they have a HTTP header there? Are they a HTTP request? Cool. Then we need to punch a hole on that HTTP header and then write the trace parent string, that big string. Too easy, right? But as you know, famous last words, because it's never that easy. So our first attempt was to do something like this. So here's like a TCP packet. It has all these headers, the Ethernet, IP, TCP, and then on green there you have the HTTP header. There is a helper that could be used with these programs called change head. So the idea was we extend the head of the packet, and then we find where the HTTP header starts, we push it up, and making room for our trace parent, and then we write it. Cool? Not really, because turns out the kernel, it keeps track of the original offsets or of where these headers are, the Ethernet, IP, and whatnot. So when we adjust it, the kernel also adjusts the offsets. And then when we manually copy it and push it up, we mess with that. What happens then is that when we try to send out the packet, it gets dropped. So that doesn't work. So we need to do something else. And what we do instead is we change the tail of the packet. So it's a different helper. Has a bit of downside that we need to copy all the payload down of that packet, and we inject the trace parent. Works, right? No. So we did that. The packet goes out. But so just a digression here. So the way TCP works in really small, nutshell, is that to make sure that nothing gets lost in the way, we have something called TCP sequence number. So it's basically you send a TCP packet out, and then your peer replies, okay, I've received these many bytes. This is the sequence number. So if in my traffic I've already sent out, let's say 100 bytes, then I have the original packet here that's 50 bytes. I'm just making these numbers up. And I send it out. In total, I have already transmitted 150 bytes. And then I get an ACK packet saying, okay, ACK 150. When we do this happens at the really end of the stack, of the network stack. We exchange the tail. The kernel doesn't know about that. It's just messing it. So now we're no longer, let's say, 50 bytes. We are 60 bytes. We send it out. And then in total, we have already transmitted, instead of 150, we transmitted 160 bytes. And we get an ACK, 160. And then this packet traverses up the network stack, but the kernel says, oh, but I was waiting for 150. Now this is bad, drop it. So what do we do? Well, crazy idea, I mean it. First attempt, it was an experiment. We tried to, okay, kind of fudge with the kernel. So we keep track of how many bytes we have extended throughout the TCP connection. And then when we get an ACK back, from our peer, TCP peer, we adjust that. We subtract those bytes again, and we fool the kernel. That works, but it's not very robust if you need to have like Bela running there, keeping tabs on what's going on, and if Bela goes away, then you messed up all your connections, and it's not great. So we figured out a more robust approach. So I was telling you about the BPF has different kinds of programs. So far we've been using one that's prog type scat CLS, so the classifier program. But there is a different kind of BPF program called socket filter. So that's the first one there, SKMSG. So this program sits very high up on the data path of the packet on the network stack. We cannot write package data, so we cannot mess with the contents of the packet, but we can add space in the packet. So it lets us use a different kind of helper, so called message push data, that lets us expand the packet in an arbitrary offset. So as you see, eBPF is all about which program you're running and the set of helpers this program is allowed to use. So we do a two-tier approach, right? We use this socket message program to punch the hole we want, and then the kernel is aware of that, because once the kernel, it reached the part of the kernel where it starts dealing with the offsets of the headers I talked about before, it accounts for that. And then once we receive that down the data path on the original classifier program, all it has to do is to write a trace parent string. So that works pretty nicely. But obviously, there are some downsides here. First of all, we're looking at strings, writing data. It's all plain text, or we need to be able to parse that. So it doesn't work with encrypted traffic. There might be a way out in the long term with KTLS, so that's TLS support in the kernel. Then we could attach eBPF programs to strategic points there where we could still see the data before it gets encrypted. But that's not the case yet. And we don't have HTTP2 supported in Bela yet. We're working on that. It's a bit more complicated. So we have an alternative. So they are complementary. We want to be robust. We want to be able to propagate the trace context. And we encode the trace parent in the IP header. So that's the other idea. So the IP header, it has a few fields we cannot abuse. Okay. In the right-hand side, I have an IPv4 packet, or the layout, and this is IPv6. So IPv4 has a section called options, and IPv6 has also a section called options, but it works a bit differently because it's just a bunch of embedded headers in the layout. So what we do here, so I'm going to show you IPv4, but the same logic applies for IPv6. So here's like a pseudo simplified version of the same package. We have the Ethernet header, IPv4, TCP, and payload. And then the classifier program can also use a different helper called adjust room. This helper is specifically made for operating in these headers like IPv4 or Ethernet, and it's only done for that. You cannot adjust room on payload or TCP. So we basically insert space for a new IP option. So right IPv4, the option part of the packet goes right in sequence. So we insert that option, and then we encode the trace parent there. But we don't have a lot of space there, right? So we cannot encode everything. Cannot encode a big string or anything like that. So we had to be a bit clever about that. So we don't care about vendor info. We do not encode the span ID. We do not encode the flags. We need only 20 bytes. So basically, the way in IPv4 it's encoded is we write the option ID. So we use an option called stream ID. It's rarely used, So hopefully it doesn't conflict with anything. And then we encode the length. So we need 16 bytes. That's the trace parent that we want to propagate. And then some padding, because it needs to be a multiple of 4. But then you're wondering, okay, what about the span ID, right? Are we not passing it along? Well, we don't have to, because it's just a unique and random number. So on ingress, now we need two kinds of programs. I was only talking about egress, right, injecting things. But now we need an ingress program. So on the other end of the data path, when you're receiving the packets, we need to be able to see if there is one of those options encoded in my packet, and be able to parse it. And then on ingress, we generate the span ID at that stage. And we derive it from the TCP length on the TCP packet, the length number, and the ACK number, the infamous ACK number that gave us problems before. So 8 bytes each, together 16 bytes, and we have our span ID. And Bela remembers that, and it keeps tabs on things. So there are obviously caveats with that. We require eBPF agents or Bela to run on both sides now, whereas with injecting the trace parent on the HTTP header, it plays nicely with auto instrumentation and manual instrumentation, because you can just parse it. We can maybe, depending on your network topology, it can be stripped by network layer switchers. It doesn't work with L7 proxies because of that as well, unless it's instrumented, because then we can re-inject it. So you need to test it. Usually it works, but famous last words, as I say. We are looking into TCP, encoding these things into TCP options in the TCP header. We had a few setbacks in the past, but we figured out a different way. We're working on that to see if that works, because that would solve this. They usually don't get stripped. And this is more or less a summary of comparing both approaches. So the original HTTP header approach, it's a multi-tier approach, 2 kinds of eBPF programs. It plays nicely with standard open telemetry instrumentation, because you can inject manually your trace parent. Bela will know about it. Bela will then inject itself. Your SDK will know about it. So it's like pretty much transparent. Not suitable for encrypted traffic, and still working HTTP support. IP header, it's not compatible with standard open telemetry instrumentation, but can work with encrypted traffic, and requires instrumentation for all services involved. And finally, we just had a beta release now, 2.0, that brings all of these goodies there, but plenty of work to do. So we encourage you to get involved. Everything is open source. You can find us on GitHub, and also we have on Grafana public Slack and the Bela channel. And yeah, I guess that's pretty much it.
Any questions?
I think there's a question over there.
Can you also, if you go out, just keep it quiet so we can hear the questions?
Yeah, I'm really interested in, this
I can hear you.
Okay. Can you hear me now?
Yes.
Okay. This was awesome. Thank you very much. And I'm already using this. I really appreciate it. I am interested particularly in things that can already be auto-instrumented using the traditional stuff. Obviously, on the Bela docs, you guys talk about instrumenting, for example, Java applications. Is there something that I'm missing that there's an advantage to using eBPF in those situations? Or is it more just in cases where you can't use that auto-instrumentation because you can't get the agent in?
Great question. So the short answer is, for Java, it makes more sense to use the Java instrumentation agent by the OpenTelemetry project, because that's a feature really by the JVM where you can hook in, get a lot more details, a lot more internals, and so forth. So if you have Java and you have the chance to attach the OpenTelemetry Java agent to your JVM, then that will give you more insights than Baylor instrumentation. There are a few cases where you cannot do this. The obvious one is modern Java, you can compile to native executables. So if you do that, then there's no JVM, and then you are lucky that you have Baylor as an alternative. The other thing is a little bit more subtle. Usually you cannot have more than one agent. I mean, you can technically, but agents prevent that because, you know, they conflict. So if you already have some proprietary agent attached to your JVM, and then it refuses to let the other agent attach as well, there might be situations where also eBPF is the only way out. But if you're able to just attach the OpenTelemetry Java agent for the specific case of Java, I think it's the best option.
Awesome. That's a really great answer. Thank you.
One, three. Okay. First of all, great presentation. Thanks. I have a question about if I don't want to propagate the spans forward. For example, it's S3 call, and with S3, it's well, if you start to mess up with headers, you need also to adjust the signee things and so on, like the signs of the headers and so on. But for example, I want to match the take the insights of how long did it take from end to end. So from request to response. So can it be used only for just creating that's mapping those guys like request and response without instrumentation, and just put the spans out to some system to track those?
Sorry, can you repeat the question? It's really hard to hear you from here.
Okay. Yeah. So is it possible to map the request and response without propagating the spans inside? So for example, it's S3 calls. I want to just track the amount of time which I spent in the S3, and for sure I don't want to have the mess up with those headers because they're signed, because there is signature there. But I want to map the zero instrumentation for tracking from request to response time, just to know how much it took, and output it to some database to map it.
If I understand your question correctly, you're asking if you can map the request and response without propagating context. Is that right? Yeah. Yes, with a few caveats. Only in the I would say only in the same node, or because Baylor is what the agent is what keeps the context. So when it correlates the request and response, it has that data. But if you are shipping a request to a different pod or different node or whatever that has a different agent running there, then you would need to somehow transmit that information. That's when this comes into play. If that answers your question.
Yeah, and but by the way, can also try to map later the data from different nodes. Yeah, so if you have, like, for example, the by IP headers, like, and ports and all that stuff, just without propagation, just doing that kind of database side.
So if you have data from different nodes, then you need the context propagation. I mean, otherwise you need to, as far as I know, correlate it manually. Yeah.
Thanks.
Welcome.
Any other questions?
One more question in front. That's the last one, then we're out of time.
Thank you for your talk. Hello? Yeah, thank you for your talk. I want to understand what the agent actually can do. So I understood if I have an HTTP request, I get basically a span for the time that is spent in the service. But do I also get spans for things that the service does whilst processing my request? For example, reaching out to a database, or
So is there more instrumentation than just the ingress and the egress of the actual HTTP request, for example?
Kind of. So what we can track with Bela is only the requests time, but not only when the request gets out, but like you said, sometimes you receive that request, but then it needs to travel. There's some kind of overhead, goes into the kernel, reach your application, and then you process it, and then you send that request out. That we can track with Bela, if that makes sense. But I wouldn't say individual parts. Then that would be a bit harder. Welcome.
That's it. Big applause for
Thank you.
Fabian and Raphael.
Hey, well done. Awesome.
Alrighty. Hi, everybody. Thanks so much for coming. I've only had some awesome talks in the last hour on auto instrumentation. Was anybody still in here about those? I think they were great. Auto instrumentation is a really awesome way to generate like some really useful data, but also a lot of data. So once we've got all of that data, what do we do with it? Where do we put it? Well, that's what I'm going to talk about. This is going to be a little bit of a higher level talk. We're going to talk about some ideas, some kind of architectural concepts. We're not going to dive down into like eBPF code, as awesome as that is. Hopefully it's useful. Oh, and you can't hear me.
It's green. No, it's green.
Okay, none of what I just said is important. Now you can hear me better. Hi everybody, thanks for coming. If you're using that auto instrumentation that we saw in those previous awesome talks, you're going to end up with a lot of data. What do you do with it, right? Let's talk about that. So hi everyone, my name's really, really small down there, but my name is Josh Lee. I am a developer advocate at Altinity. We do hosting services and support for ClickHouse. So if what I'm talking about to you is interesting, come talk to me, follow me on LinkedIn, or come talk to us at our booth in building UA across the courtyard. Let's dive in. So today we're going to talk about observability in one, or Ollie in one, as I like to say, and using ClickHouse as a unified database for all of our telemetry signals. Okay, so I spent most of 2022 and 2023 really talking about OpenTelemetry both publicly and internally at my employer. And usually I start with a diagram that looks something like this. It's very familiar, I'm sure, to all of you from like the OpenTelemetry documentation or just any blog post that you've read about OpenTelemetry. And the simplicity of this diagram is really useful for explaining the architecture of OpenTelemetry to someone who's never encountered it before. But it is very misleading, and it misrepresents the complexity of how we're actually using OpenTelemetry in our real-world applications, right? So one of the things that's on, sort of proudly placed on the OpenTelemetry website, so as to not, I think, compete with the vendors that are supporting OpenTelemetry, the OpenTelemetry project does not include any kind of database or backend UI. That's sort of just up to you, right? And then we also have this piece of information from the Grafana State of Observability report. Thank you, Grafana folks. 6 is a typical number of observability tools that an organization will have deployed in production, right? And I don't mean like Fortune 100 organizations here. I mean any organization. So what I think we actually need, if we kind of take that first graph that we were looking at and actually just reverse it, we get something that looks more like how we actually would want to think about observability in the real world. Some of, on the right, or sorry, all the way there on my right, on your left, we have some of my favorite sources of telemetry data. You're probably using some combination of all of those today in your organization. We then need to consolidate, right? We want to take that and, in order to process that information and correlate it correctly in the way that we want, build the topologies that we want, build the dependency graphs that we want, we need some way to combine all of that information, and then ultimately we need to store it so that we can use it for things like alerting and dashboards and analysis. So I think this diagram is more realistic than the one that we just had. And there are more challenges, right? If we're splitting up our telemetry data, now technically you could build a unified observability solution with a separate database for each signal, but you might not want to, right? But if you don't have that unified, without that unified interface, right, without one way to view all of your data, when you have to go to different tools for your different types of data, different signals from different sources, you run into problems, right? We're all very, very smart and good at our jobs, but the more times you have to like correlate an ID from one tool to an ID from another tool and like basically do all of the joins in your head, just every single one of those little points of friction is a chance to make a mistake when you're in a really stressful scenario trying to respond to a production outage, right? And it's like, we can't afford mistakes. So ideally, we should be reducing all of the opportunities for mistakes, and instead we don't, right? Like we have this like setup where we need 8 different monitors to respond to a production incident. It's kind of crazy. We got a lot of haystacks to look through, right? But when we look at what actually goes into those haystacks, right? Like what are we actually storing in our telemetry databases? Of course it's the signals, right? It's the metrics, traces, and logs, soon profiles and events, right? OpenTelemetry is adding more signal types. It's not 3 pillars, and that's awesome. We need all of these different data formats to structure the data in the way that's useful and compressible for the thing that the questions we're trying to answer. So that's gonna be the bulk of your data, and that's gonna be the bulk of your queries. But there's more stuff than just that, right? We also need the resource metadata. Resources, for those not familiar with the OpenTelemetry terminology, it's really just the metadata that describes the entities, right? So the node that the process is running on, the process, things like that. Maybe the EC2 region that the node is in, right? Things like that would all go in your resource metadata. And all of that information is useful because it allows us to tie together, right, those telemetry signals and contextualize them and make sense of them and what they actually relate to. Then from all of those relationships, we can actually create graphs and topologies of, right, we can create dependency topologies, we can create topologies like James showed two presentations ago that show sort of the entire architecture of our application. These are really, really useful. At scale, right, when we talk about really, really large organizations, one of the hardest challenges is just zeroing in on the data that you care about. And it turns out that if you have a topology as sort of the front of your filter, that's a really good way to filter down to the specific data that you care about. Of course, if we have graphs and topologies, those are kind of expensive to calculate. So we're going to want to store them and maybe hang on to them for a certain period of time. So we're going to have some kind of snapshots. If we have snapshots, it makes sense that we might have some concept of deltas in order to efficiently store changes in those snapshots. And then finally, right, of course, we need configuration. We need users. We need the dashboards, all the stuff that actually is probably fine in like a traditional OLTP database. Whereas, you know, if you're trying to use an OLTP database for these other things, you're going to run into some scaling problems. You're going to run into some performance problems. Okay, so we can't use OLTP. Is there a silver bullet? Is there something we can use? Well, no. If there was a silver bullet, right, like Honeycomb wouldn't have to build the custom storage engine that they have for their really cool high cardinality stuff. We need all of these things, right? We need the ability to do full text search. That's really important for logs. We need really efficient compression. That's important for everything, but especially for logs and metrics, right? We need the ability to query in real time, more or less, and get real-time analytics on the data as it's coming in. We need to be able to alert quickly, like on the order of seconds, not minutes or hours, on any variations in that data. We need to be able to relate the data to other parts of the data. And at enterprise scale, right, we're talking about a metric ton of data, right? So we need this solution to be petabyte scale. So while there is no silver bullet, ClickHouse comes pretty darn close to checking all of those boxes. So I think it's a pretty good starting point. So let's talk about ClickHouse. Raise your hand if you are already familiar with ClickHouse or using it. Wow, awesome, okay. That's not the response I'm used to, but I love it. So ClickHouse, really quickly then, ClickHouse is SQL compatible. It is extremely massively scalable, both horizontally and vertically. And it is really, really, really fast, like sub-second queries on petabytes of data, and ingesting millions of rows per second is absolutely no problem. And it's really, really powerful for observability use cases specifically. And I'm going to talk about why that is and how the architecture of ClickHouse lends itself to observability use cases. So all of that data that we were looking at a couple of slides ago, right, the metrics, traces, logs, profiles, events, all that fun stuff, it follows a worm pattern, right? Once, read many. It doesn't change, right? A log line is a log line, a trace is a trace. We never need to update it. So we need to write it, store it, hold on to it for a certain amount of time, whatever our retention period policies are, right? And probably query it, read it a ton of times during that lifetime. Hopefully, if you're not reading it, then like, why did you collect it? But that's a different problem. Eventually it'll get deleted sort of as a part of a bucket, but we don't ever need to update it along its lifetime. When we think about this kind of data, maybe we think about balanced trees. Balanced trees are really great for really, really quickly reading all of that structured data, but they're really expensive when it comes to like inserting the data because you have to reorder and reorganize everything and rebuild your entire tree every time you do an insert. Not great for tracing data where you're going to be getting 60 spans for one WordPress query. So we have a solution for this. And one solution, this is what Elastic uses, is log structured merge trees. So this is optimized for ingestion, and how we do this is we store key value pairs buffered in memory, right? And we keep these really short little bits of data, and then we can order them. And then once they're sorted and ordered, right, we can flush those to the disk. We can immediately query them and use them as part of our read operations. And in the background, we can compact them, right? So we can make them bigger and bigger, maintaining the order so that the read operations are still really fast and efficient, but also making better use of storage and better use of our nodes and speeding up those reads even further. This is really, really cool. This is a great blog post from Ben Stepford. It goes into more detail on how this works in Elastic specifically. It's a little bit different in ClickHouse. So in ClickHouse, instead of storing key value pairs and compacting them, we're storing entire columns, which if you think about like time series data or basically any type of observability data, this is going to allow us to do the types of reads that we need to do as quickly as possible. There is a way to update and delete in ClickHouse. I'm not going to talk too much about that today, but it's possible if you do need to do that. And then we have the same thing that we saw in Elastic, right? We have these unmerged parts getting compacted into larger and larger parts that can be queried more and more efficiently. This is happening over the course of minutes in the background, right, as the data is inserted. So how does this help us, right? How does this data structure help us do observability better? Well, one thing it gives us, right, we mentioned it makes it very efficient. We get very fast writes because we can just dump whatever data we have straight into memory and then let the nodes sort of figure it out. It's very time friendly, right, because we're ordering the data usually on the time stamp, right, that the telemetry signal came from. This format lends itself to that ordering very well. We get very easy cleanup through TTL policies. Again, because everything is ordered by time, we can just drop off an entire one of those partitions and handle our TTL. And since that data is all ordered, it's very compressible, right? And that makes it very cost effective for us. ClickHouse also has some more features that lend itself to observability use cases. I like to say that you can almost build an entire application inside of ClickHouse using all of the features that are available. So we have materialized views. These allow us to transform data from one format into another. You might use these, for example, to take OpenTelemetry spans, or I don't know, take Zipkin spans and cast them to OpenTelemetry spans. It's the same data, right? Just slightly different keys. You can do much more powerful things with that, but that's a pretty common observability type use case. I mentioned we have time to live, so we can build in the expiration of data, build in policies. We can also migrate data from hot storage to cold storage using things like S3 or other object storage. So we can use that to control our costs as well. We can use this on-premise, so we can keep data, right? Like I was talking to someone yesterday who keeps 10 years of their log data in some cases. I'm sorry, but you definitely don't want to do that with Datadog. Yeah, so we tiered storage. Okay, and then integrations, right? Like this is SQL compatible, so that just basically opens up the door to integrate with pretty much anything. There's actually 2 Grafana data source plugins. One is maintained by Altinity, by us. It has some nice little macro helper functions in it to help you create time series data out of stuff that wasn't originally time series data and make it look really nice in your Grafana dashboards. Jaeger, which is a popular trace visualization tool, supports ClickHouse as a backend. Right out of the box, you just have to say, yep, I want to use ClickHouse and give it an instance. There's CLoki, which is actually evolved into Quarian, which I'll talk about in a little bit. And there is a Kafka table engine for ClickHouse. So if you're one of those organizations that already has all of your observability data on a Kafka stream, you can just point that Kafka stream at your ClickHouse database, and boom, all of your observability data is persisted. So we end up with something that looks kind of like this. Oh, right, there's an OpenTelemetry exporter for ClickHouse, right? So this goes in the collector or in your OpenTelemetry SDKs. It currently supports traces, metrics, and logs. Support for the other signals will be coming soon. And so through that, then we get access to not just like those 6, like my favorite things over there, but all of the 90+ receivers from the OpenTelemetry ecosystem are now available to us as data sources that we can pipe directly into ClickHouse. Cool. Okay, so more benefits. We get excellent compression, even with variable schemas. So we're taking all of these disparate sources. We don't have to know ahead of time what schemas we're dealing with. We don't have to build that into ClickHouse. We can use sort of arbitrary maps and JSON columns, and we can still take advantage of some of the excellent compression and really fast reads that ClickHouse is going to give us. It'll even, like inside a JSON map column, turn those into columnar storage parts. We get practically unlimited cardinality. So Cloudflare gave a great talk at Monodrama last year where they mentioned, it talked about moving from Prometheus to ClickHouse for time series data. Anyone run into cardinality issues in Prometheus? Yeah, okay. No one even wants to raise their hand for that, but I know you all have. Low cardinality in Prometheus, right? Low cardinality, everything's relative. In Prometheus, it means like dozens, maybe scores, right? Okay, in ClickHouse, low cardinality means millions. So we're talking about completely unrelated orders of magnitude when it comes to cardinality. That's really, really useful too for this sort of arbitrary observability data where we don't necessarily have control over all of it on the front end, right? We're part of an SRE team or some team that's managing all of this data, but there's a ton of other teams generating the data and we can't control what they do. So cardinality is one of those things that's actually really, really hard to control. It's going to drive your costs up with some of those vendor tools. But with ClickHouse, you can kind of worry about it less. You still do have to worry about it, just a lot less. And like I mentioned at the beginning, right, it's extremely horizontally scalable, both for ingestion and for reads. So this is great for observability, because we can scale up to meet our own needs, whatever those may be. There are some challenges, though. It's not perfect. It doesn't solve all of our problems, right? Nothing does. One of the biggest challenges that people run into using ClickHouse for observability is that SQL is not PromQL. And people who spend most of their time dealing with observability data tend to really like PromQL, right? Like it's a very productive, very terse language for the types of queries that it handles. Asterisk there, because both at Altinity and at ClickHouse Incorporated, there is work underway currently to bring PromQL support to ClickHouse. So you can just write PromQL queries. Yeah, wouldn't that be awesome? And then that opens up like even more integrations, right? Like think about all the tools that integrate with PromQL, then you can just use those with ClickHouse. Makes your Grafana dashboards easier. It makes Persis integration possible. So this is really cool. Okay, another challenge with ClickHouse is that some people say that it can be overly complex for small data volumes. This bullet point comes more or less directly from the ClickHouse Inc. blog on observability with ClickHouse. I kind of disagree. I've spoken to we have some customers who are dealing with, tens of gigabytes of data on ClickHouse. And because of all of those features that we were talking about, right, they find that it's worth it, even though they're not dealing with the scale that ClickHouse was sort of originally built for. So you can use this at any scale. And then another thing I would say is like, I've gotten 150 gigabytes of observability data out of like a demo running on a Raspberry Pi for a few days. So what is small, right? Everything's relative. And then one final challenge with ClickHouse, it's just a database, right? It's not a complete observability solution. It doesn't have any alerting. It doesn't have any visualization. It has integrations with all those things, and that's great. But by itself, it is by no means a turnkey solution. It's just a storage engine. We do need that, though, right? We need that for observability. We need both a database and a back-end UI of some kind. We need a complete observability solution, right? So here's kind of my simplified diagram of what a complete observability solution might look like. You've got your application SDKs, right? OpenTelemetry is awesome for that. You've got your host and node agents. OpenTelemetry is also awesome for that.